Hello there and welcome to Physics with William, where the universe is allowed to be a little strange, a little quiet, and just interesting enough to keep the mind company as the rest of you begins to settle down. Tonight, we are turning our attention to something so small that it cannot be seen even with the most ambitious ordinary imagination, and yet it has helped shape some of the deepest ideas in modern physics. We're going to spend some time with the meson, a particle that sounds almost modest when you first hear its name, as though it might be a minor supporting character in the story of matter. But the deeper you look, the less modest it becomes. A meson sits in that curious subatomic territory where the rules feel familiar for a moment and then quietly stop behaving. At first glance, the question sounds simple enough. What is a meson really made of? You might expect the answer to arrive neatly wrapped, like the label on a tea tin or the ingredients on a biscuit packet. Perhaps it is made of one tiny thing, or another tiny thing, and that is the end of it. Physics does not always grant us that kind of tidy ending. The closer we get to the foundations of matter, the more often the word made begins to wobble. In daily life, made of seems straightforward. A chair is made of wood. A mug is made of clay. A blanket is made of fabric. But down in the particle world, being made of something is not always like bricks in a wall. It can also mean held together by invisible fields, shaped by restless motion, surrounded by transient activity, and defined as much by interactions as by ingredients. That is where the meson becomes especially interesting. It is not only a thing, it is also an eventful little arrangement of deeper things, constantly alive with internal drama. Before we go any farther, I would love to know where you are listening from tonight and what sort of hour it is in your little part of the world. Is it late enough that the room has gone mostly quiet? Is there rain on the windows or traffic still muttering outside, or one determined refrigerator making itself known from the kitchen? There is something fitting about asking that at the beginning of a discussion like this, because particles do not care much about our clocks, and yet here we are, meeting them from bedrooms, sofas, dim desks and nighttime headphones, each of us arriving from a different scale of reality entirely. And if this sort of gentle wandering through physics is the kind of thing you enjoy, if it helps you unwind or gives your thoughts something calm to follow, do consider liking the video and subscribing. It helps this small corner of scientific curiosity find other people who may also want a quieter way into big ideas. Though I should warn you, the subatomic world has a habit of sounding sleepy right up until it does something outrageous. Now, when most people first hear about the building blocks of matter, the story begins with atoms. That seems reasonable. Atoms feel like the right size for a basic unit of reality. Small enough to be impressive, large enough to be imaginable. Then the story gets more ambitious and says that atoms themselves are made of electrons around a nucleus, and inside that nucleus sit protons and neutrons. By this stage, it still feels manageable. Tiny objects inside larger tiny objects, a neat nesting doll arrangement. But then physics keeps going, and the simple picture begins to fray. Protons and neutrons are not elementary either. They are built from quarks, held together by gluons, inside a theory so successful and so bizarre that it can sound almost perfectly reasonable until you pause and actually think about what it is claiming. That is where the meson enters the room. A meson is not like a proton, though the two are related. It is not like an electron either, though that comparison is also useful for a while. A meson belongs to a broader family called hadrons, particles that are built from quarks and governed by the strong interaction. If that already sounds like the answer, we are only at the outer wrapping, because saying a meson is made from quarks is a bit like saying weather is made from air. True, but not nearly enough to explain what is really going on. The simplest description of a meson is that it is made of a quark and an antiquark bound together. That is the phrase you will often meet first, and it's a good place to begin because it captures the essential structure without too much clutter. One quark, one antiquark, held together by the strong interaction. Simple, respectable, almost suspiciously tidy. The trouble is that in modern physics, simple descriptions are often the doorway rather than the destination. A meson is not just a quiet pair sitting politely beside one another, like guests at a formal dinner. Quarks inside particles are energetic, confined, and deeply entangled with the fields around them. Gluons are constantly involved, not as an occasional adhesive, but as an active and relentless part of the whole arrangement. And around that quark-antiquark pair, the vacuum itself is not empty in the ordinary sense. It seethes with fleeting contributions, temporary disturbances, and quantum activity that make the idea of a fixed, static interior feel far too calm. If that sounds like physics is trying to make life difficult, I promise it is not being deliberately unhelpful. It is just that the world at very small scales turns out not to resemble the world of marbles, gears, and stacked boxes. We like the language of objects because it makes us feel steady. This thing is made of that thing, end of story. But a meson behaves less like a tiny bead and more like a dynamic bound state. It is defined by what is there, yes, but also by how what is there behaves. Imagine asking what a song is made of. You could say notes, and that would be true, but it would miss rhythm, timing, resonance, relation, and motion. A meson is a little like that. Its identity is not only in its contents, but in the pattern those contents form under the rules of the strong interaction. The word meson itself has an interesting feel to it. It comes from a root meaning middle, because when these particles were first discussed, they seem to occupy a middle ground in mass between electrons and heavier particles like protons. That naming made sense at the time, and like many scientific names, it preserved a snapshot of how people first met the idea. Science often works that way. A label begins as a practical guess, a bit of descriptive convenience, and later the theory deepens beneath it. By the time we understand the thing properly, the name may be a little old-fashioned, but it stays on like a street name surviving long after the original shopfronts have vanished. One of the reasons mesons matter so much is that they played a key role in helping physicists understand the strong force, the interaction that binds atomic nuclei together and keeps quarks confined inside larger particles. In fact, mesons have worn more than one explanatory costume in the history of physics. At one stage, they were thought of partly as messengers of the force between protons and neutrons in the nucleus. Later, with the development of quark theory and quantum chromodynamics, the picture became deeper and stranger. Mesons did not stop being important. They simply acquired a richer and more precise identity. That happens often in science. A useful picture does not always vanish when a better one arrives. It gets absorbed, reinterpreted, and set into a bigger frame. Now, if you are half tempted to ask why nature bothers with mesons at all, that is a very sensible question. Why should a quark and an antiquark bind together into a short-lived particle, instead of just wandering separately through the universe? The answer, in a way, is that they cannot wander separately, at least not under ordinary conditions. Quarks are confined. This is one of the most remarkable features of the strong interaction. Unlike electric charge, where isolated positive and negative charges can exist on their own, colour charge, the charge associated with the strong force, behaves differently. Pull quarks apart, and instead of the force fading gently with distance, the connection resists separation so strongly that new particles can form from the energy involved. Nature in this domain seems to prefer bound states. Mesons are among the simplest such states, but simple here does not mean trivial. It is worth slowing down over the antiquark for a moment, because antiparticles can sound more dramatic than they need to. An antiquark is not a magical anti-object from a sinister mirror universe. It is a perfectly real partner to a quark, with opposite values for certain properties. When a quark and an antiquark come together, they can form a meson. Depending on which kinds of quark are involved, you get different members of the meson family. Some are light and relatively common in high-energy interactions. Some are heavier and more exotic. Some live only for astonishingly brief intervals before transforming into other particles. If human introductions were this short, Dinner parties would be much more efficient. What makes this especially interesting is that Mesons are not just obscure decorations on the edge of physics. They are part of the ordinary machinery by which particle physicists test theories, study interactions, and understand how matter behaves under extreme conditions. When particles collide at high energies, mesons are often among the debris produced. They appear, decay, and leave behind clues. They are not permanent residents of everyday visible matter in the way electrons and protons are, but they are absolutely part of the universe's vocabulary. To study mesons is to learn one of the dialects in which nature speaks about quarks. There is also something conceptually useful about mesons because they sit in a kind of sweet spot. Electrons are treated as fundamental in the standard model. Protons and neutrons are composite objects with 3 valence quarks. Mesons, with their quark-antiquark structure, are in some ways simpler than those heavier composite particles, and in other ways more slippery because many of them are unstable and deeply shaped by the dynamics of the strong force. They give physicists a manageable but still richly complicated laboratory for testing ideas about confinement, binding, decay, symmetry, and the behaviour of quantum fields. In calmer language, they are a very good place to see the subatomic world misbehave in instructive ways. Still, to ask what a meson is really made of is to ask for more honesty than the introductory description usually gives. If we answer only with quark and antiquark, we risk giving the impression of a tiny binary object, something like 2 peas in a pod, perhaps with a dab of gluon between them like glue on a craft project. That is not the picture modern physics supports. The gluons are not a side note. They are essential carriers of the strong interaction, and because they themselves carry the relevant charge, they can interact with one another as well. This makes the whole business much richer and less intuitive than forces that merely pass messages and retire politely. The inside of a hadron is a roiling quantum system. Even the vacuum around it is active in a way that common language does not prepare us for. Virtual quark-antiquark pairs can briefly contribute. C-quarks can matter. The distinction between the main ingredients and the surrounding activity is useful, but not absolute. That is one reason particle physicists often distinguish between valence quarks and the C. The valence quarks are the ones that define the basic identity of the particle. In a meson, that means the quark and antiquark pair that give it its main quantum numbers, but inside there is more going on. Gluons can split and contribute to temporary quark-antiquark pairs. The particle is not a dead arrangement. It is a fluctuating system described by quantum fields. So if you ask what a meson is really made of, the most careful answer is not merely a quark and an antiquark, but a quark-antiquark bound state, immersed in strong force dynamics, with gluonic activity and quantum fluctuations contributing to the full physical picture. Which is perhaps not the sort of answer one casually tosses into conversation over toast, but it is closer to the truth. Another useful thing to notice is that the word made can tempt us into imagining a meson, as if it were assembled from tiny solid components that keep their ordinary identities at all times. But quarks in bound states do not behave like miniature pebbles. They are excitations of underlying fields, described by wave functions and probabilities, confined within a region where momentum, energy, and interaction are inseparable from the structure itself. If this feels slippery, that is because it is. The deeper physics goes, the less the old distinction between object and process holds its shape. A meson is not just built. It is maintained by the rules of the theory. Its existence is an ongoing act of balance among field excitations, interaction energy, confinement, and allowable quantum states. And yet, for all this complexity, mesons are not vague or imaginary. They are measurable. They have masses, lifetimes, decay products, and characteristic behaviours. They show up in detectors. They can be predicted, categorised, and studied with remarkable precision. Physics at its best often feels like this strange mixture of certainty and unease. We know a great deal, enough to build experiments, confirm models, and make successful predictions. but the concepts underneath what we know resist being translated into simple, everyday pictures without losing something important. Mesons are real, very real. But the way they are real is not especially homespun. There is also a charming irony in the fact that some of the most fleeting particles have taught us some of the most lasting lessons. Many mesons decay quickly. Some survive for only a tiny fraction of a second. But in that brief span, they reveal the structure of the strong interaction, the organization of quark flavors, the role of symmetries, and the pathways by which unstable states transform into others. They are less like permanent bricks and more like informative sparks. You do not need them to last long for them to say something profound. So as we settle into this question, it helps to hold two versions of the answer at once. The first is the clean one, the one you might say if someone asked while the kettle was boiling. A meson is made of a quark and an antiquark. The second is the fuller one, the one that keeps physicists up later than they intended. A meson is a strongly bound quantum state whose defining quark-antiquark structure exists within a constantly active field environment shaped by gluons, confinement, and quantum fluctuations. Both are true. One is a doorway, the other is the room beyond it. And this is where the story becomes especially interesting, because mesons did not arrive in physics as neat textbook examples. They emerged through confusion, prediction, detection, misidentification, and a gradually widening sense that the subatomic world was far more crowded than anyone had hoped. Before quarks became part of the language, before the strong interaction was given its modern form, physicists were already stumbling into a growing population of unfamiliar particles and trying to make sense of what sort of hidden order, if any, tied them together. The meson was not simply discovered and understood in one clean gesture. It had to be approached through the long, slightly untidy history of what became known as the particle zoo, where every new experimental result seemed ready to complicate the furniture. To understand why mesons mattered so much, it helps to step back into a period when physics was beginning to lose the comfortable simplicity it once thought it had. There was a time when the list of known particles felt almost manageable. You had the electron, already well established as a light and negatively charged component of atoms. You had the proton, sitting in the atomic nucleus and carrying positive charge. Later came the neutron, which helped explain why nuclei could contain more mass than charge alone seemed to allow. For a brief and rather hopeful moment, it looked as though the subatomic world might be built from only a small cast of characters. Matter seemed spare, almost elegant. A few particles, a few forces, a bit of clever mathematics, and perhaps the universe would politely give up its structure. That optimism did not last. Once experimental tools improved and cosmic rays began to reveal events from high-energy processes in the atmosphere, physicists started seeing tracks and interactions that did not fit the familiar trio of electron, proton, and neutron. New particles appeared as if nature had been keeping a second inventory somewhere out of sight. They arrived not in a calm, orderly line, but in a confusing stream. Some were heavy, some were unstable, some lived for only tiny fractions of a second. Some behaved similarly enough to known particles to invite premature guesses, but differently enough to ruin those guesses almost immediately. It was not yet clear whether these newcomers were fundamental, composite, rare curiosities, or symptoms of a theory that had not caught up with experiment. This was the beginning of what physicists later called the particle zoo, and the name was not entirely affectionate. It carried a hint of exasperation. A zoo is full of creatures, but it's not always obvious at first glance how they are related. There are categories, yes, but also oddities, exceptions, and beasts that seem designed specifically to embarrass tidy classification. That was the feeling in particle physics through the middle decades of the 20th century. The deeper researchers looked, the more the subatomic world seemed crowded. Each new collision, each cloud chamber photograph, each unexpected decay event threatened to add another resident to the growing collection. The methods of the time contributed to the drama. Many early discoveries did not come from purpose-built giant colliders of the sort people imagine today. They came from painstaking examination of tracks left by energetic particles in cloud chambers, bubble chambers, photographic emulsions, and other detectors that translated invisible events into visible traces. A charged particle would pass through a medium and leave behind a path. That path might curve in a magnetic field. It might suddenly fork. It might stop and give rise to secondary tracks. Physicists became, in a sense, detectives of curved lines and brief disruptions. They had to infer identity from motion, mass from curvature, energy from geometry, and decay from track patterns. It was careful work, and sometimes nature was not especially interested in being easy to read. Cosmic rays played a major role in this story. Long before colliders could routinely create very high energies in the laboratory, the universe was already doing it overhead. Particles from space were striking the upper atmosphere and producing showers of secondary particles. Some of these reached detectors on Earth or at high altitude. For physicists, this was both a gift and a nuisance. The gift was access to energies not otherwise available. The nuisance was that cosmic rays arrived on their own terms at unpredictable times with limited control over initial conditions. It was rather like trying to understand the mechanics of a machine by examining pieces thrown at you from a great height by an invisible assistant. Still, the information was too valuable to ignore. One of the earliest important clues in the history of Mesons came from theory before experiment had fully caught up. In the 1930s, Hideki Yukawa proposed that the force-binding protons and neutrons inside the atomic nucleus might be carried by a new kind of particle. This was an extraordinary suggestion because it turned a question about nuclear cohesion into a question about exchange. The nucleus was known to be tightly bound, but the mechanism was unclear. Electromagnetic repulsion should push protons apart, and yet nuclei held together. Yukawa reasoned that a massive intermediary particle could produce a short-range attractive force, unlike the long reach of electromagnetism. The predicted particle would have a mass somewhere between that of the electron and the proton. That middle range gave rise to the term Meson. Now, once a theory predicts a new particle, experimentalists become highly motivated in a way that is both admirable and occasionally risky. When something unusual appeared in cosmic ray data, there was a natural temptation to match it to Yukawa's predicted nuclear messenger. In the late 1930s and early 1940s, a particle was indeed found with a mass in roughly the expected range. It seemed for a moment that the hunt had succeeded. The new particle was first welcomed as the long-awaited Meson. Unfortunately, nature had other plans. The particle that had been found was not behaving like Yukawa's nuclear force carrier should. It did not interact strongly enough with nuclei. It penetrated matter too readily. It looked Meson-like in mass, but not in function. It was eventually recognized as a different particle altogether, now called the muon. The muon was a remarkable discovery in its own right, but it was not the answer to the original nuclear puzzle. This misidentification is one of the reasons the early history of the particle zoo feels so human. Theoretical expectation and experimental evidence met each other, shook hands, and then realized they had been introduced under false names. There is a famous reaction associated with the muon's arrival into physics, often paraphrased as "who ordered that?" It captures the mood perfectly. The muon did not solve the problem people wanted solved. It simply existed, insistently and inconveniently, adding to the list of known particles without making the bigger pattern any clearer. Science sometimes advances this way. You do not get the answer you expected. You get an extra question with a measurable lifetime. The actual particle more closely connected to Yukawa's idea turned up later, and with better evidence. This was the pion, one of the lightest mesons and historically one of the most important. The pion did interact strongly, and played a major role in the effective description of nuclear forces between protons and neutrons. Here at last was a particle that resembled the mediator Yukawa had in mind, though later developments in quantum chromodynamics would place the deeper explanation elsewhere. Even so, the pion's discovery was a major step. It showed that the strange growing population of unstable particles was not just experimental clutter, There was genuine structure hidden inside the chaos. Still, the zoo kept expanding. Alongside pions came kaons and a whole collection of heavier unstable particles. Some were produced easily enough in high-energy collisions, yet decayed unexpectedly slowly compared with what their production mechanisms suggested. This led to the introduction of new quantum numbers to keep track of what was being conserved in some interactions but not in others. One of the most famous of these was strangeness, a name that remains one of the more honest labels in physics. When particles behave in a way that seems odd relative to existing categories, calling them strange is not the most elegant theoretical move, but it is at least emotionally accurate. The strange particles were especially troublesome because they seemed to be created through strong processes but decay through weaker ones. In practical terms, they arrived quickly and left slowly. That mismatch forced physicists to recognize that not all interactions were governed by the same rules or the same timescales. It also hinted that particle identity involved hidden properties not immediately obvious from mass and charge alone. The subatomic world was developing personality traits, and classification was becoming a serious business rather than a simple list-making exercise. By the 1950s, particle physics had become crowded enough to feel almost alarming. New resonances and unstable states were appearing in accelerator experiments as well as cosmic ray studies. Bubble chambers produced beautiful photographs of particle tracks, but each beautiful event also threatened to create a new bookkeeping problem. If you're trying to discover the laws of nature, there is a certain point at which finding more and more apparently unrelated particles begins to feel less like progress, and more like being buried under evidence. Physicists were not just collecting residents for a zoo anymore. They were trying to understand whether the zoo reflected a deeper order, or whether matter itself was far more untidy than anyone had hoped. This pressure produced some of the most important conceptual work in the history of modern physics. Researchers began looking for patterns among the particles the way chemists had once looked for patterns among the elements. Were there families, multiplets, hidden symmetries, recurring structures beneath the clutter? Instead of treating every newly discovered particle as a fully separate fundamental object, physicists started entertaining the possibility that many of them might be related through deeper organizing principles. The zoo might not be a random menagerie after all. It might be a taxonomy waiting to be decoded. That effort led to classification schemes based on properties such as charge, spin, mass, and newly introduced quantum numbers. Mesons and baryons emerged as broad categories within the hadrons, the strongly interacting particles. Baryons included particles like the proton and neutron. Mesons formed another group, generally lighter and often unstable, with their own internal structure still not fully understood at that stage. The distinction itself was useful, but the bigger breakthrough came when symmetries began to reveal order among the proliferating particle states. One of the key moments was the development of the Eightfold Way by Murray Gell-Mann, and independently Yuval Neeman. This framework organized hadrons into symmetry patterns that strongly suggested they were not all fundamental. The patterns were too neat to be accidental. Much like the periodic table hinted that chemical elements obeyed a deeper logic, the Eightfold Way suggested a more basic level of structure beneath the hadrons. It did not immediately prove what that structure was, but it made the search much sharper. Once you see a pattern, it becomes difficult to believe the pieces are unrelated. That line of thinking helped open the door to the quark model. Gell-Mann and Zweig proposed that hadrons could be understood as combinations of more elementary constituents. In this picture, baryons were built from 3 quarks, while mesons were built from a quark and an antiquark. With that proposal, the particle zoo began to look less like a sprawling collection of unrelated animals, and more like a set of composite arrangements built from a smaller underlying alphabet. The mess had not disappeared, but it had become legible. It is hard to overstate how transformative this was. Once mesons could be interpreted as quark-antiquark states, a huge amount of confusion began to settle into structure. Different Mesons were no longer merely separate discoveries. They became distinct combinations of quark flavor, spin arrangement, and interaction dynamics. Pions, kaons, and other mesons could be placed into families with understandable relationships. The same was true for baryons. Even particles that had seemed especially strange now fit into a more coherent framework. Strangeness itself became less a mark of conceptual irritation, and more a clue to the presence of a strange quark in the underlying composition. Even then, the story did not become simple overnight. Quarks themselves were initially a bold and somewhat controversial idea. They carried fractional electric charges, something never observed in isolation, and no free quark had ever been seen. That made some physicists cautious. Were quarks real physical constituents or merely mathematical devices for organizing the hadron spectrum? This was not a small question. A successful classification scheme does not automatically guarantee that its building blocks are literal residents of reality. Sometimes a model works because it captures structure without naming actual components. Over time, however, evidence mounted that quarks were more than bookkeeping conveniences. Deep inelastic scattering experiments probed the interior of protons and revealed point-like constituents behaving much as the quark model suggested. The development of quantum chromodynamics then provided the field theory of the strong interaction, with quarks carrying color charge and gluons mediating the force between them. Mesons and baryons became natural bound states within this framework. The zoo had not been eliminated exactly, but it had been reinterpreted. Many of its occupants were no longer thought fundamental. They were composite states arising from the dynamics of quarks and gluons. There is something pleasing about that historical arc. The early sense of chaos was real. Physicists were not foolish for feeling overwhelmed by the growing particle list. The data really did look unruly. But the unruliness was not the end of the story. It was the visible surface of a deeper order not yet recognized. What seemed like a wild accumulation of unrelated creatures turned out to be the expression of an underlying theory, with symmetries, constituent structure, and rules of interaction far more elegant than the raw list of particles first suggested. Mesons, in that history, occupy a particularly revealing place. They were central to the early effort to understand nuclear forces. They were part of the confusion of mistaken identities that included the muon. They became essential members of the growing hadron families in the zoo years, and later they emerged as some of the clearest examples of quark-antiquark bound states. If you follow the history of the Meson, you are really following the history of particle physics, learning how not to mistake abundance for disorder. Nature was not being excessive for the sake of it. It was showing many faces of a smaller set of principles, and yet the zoo never entirely vanished as an idea, because even after the quark model brought order, new hadronic states kept appearing. Some of them fit neatly into the expected Meson and baryon categories. Others have been more difficult to classify, raising questions about tetraquarks, pentaquarks, hybrid states, and gluon-rich configurations. So the lesson of the old zoo period still has a modern echo. Every time physics thinks it has fully organized the collection, nature reserves the right to produce something slightly awkward. That is not a failure of the theory. More often it's the sign that the theory is alive and still being tested where it becomes most interesting. For now though, the crucial turn in the story is this one. The particle zoo looks strange because physicists were seeing many bound states before fully understanding the constituents and forces that produced them. Once quarks entered the picture, mesons stopped being mysterious standalone animals and became combinations with a pattern. That does not mean they became dull. Quite the opposite. Once you know that a meson is built from a quark and an antiquark, the next question becomes immediate. What exactly is a quark in this context? What makes one flavor different from another? And how can a particle and its opposite partner bind so tightly that they form something entirely new? So once the particle zoo began to look less like a collection of unrelated surprises and more like a pattern waiting to be read properly, attention naturally shifted toward the pieces underneath it. If mesons were not fundamental after all, then what were their ingredients? What kind of thing was a quark? What made an antiquark its partner? And why did nature seem so willing to pair them into brief but meaningful particles that flashed into existence, lived according to very strict rules, and then disappeared into something else almost before the experimental apparatus had finished noticing them? The word quark has one of those wonderfully improbable origins that make science feel slightly more human than its reputation suggests. Murray Gell-Mann borrowed it from a line in literature, and somehow that odd-sounding word became the label for one of the deepest ingredients in the standard model of particle physics. At first glance, quarks do not sound especially dignified. They sound as though they might belong to a mechanical toy or a slightly offended waterbird. But the things themselves turned out to be central to the structure of matter. Once physicists began taking quarks seriously, they were no longer just useful placeholders in a classification scheme. They became the entities that explained why hadrons came in the groupings they did, why certain symmetries worked so beautifully, and why mesons and baryons could be organized with such consistency. A quark, in the modern sense, is an elementary particle. That means, as far as present evidence shows, it is not made of smaller known pieces in the way a proton is made of quarks, or an atom is made of a nucleus and electrons. It has intrinsic properties such as mass, electric charge, spin, and a special kind of charge associated with the strong interaction called colour charge. The word colour here is historical and metaphorical. It has nothing to do with visual colour. No one is peering into a detector and spotting a blue quark drifting past like a subatomic berry. The name was chosen because 3 kinds of colour charge are needed in the theory, and the analogy gave physicists a way to talk about them. This is one of those places where particle physics sounds whimsical while being deadly serious underneath. There are several kinds of quarks, known as flavours: up, down, strange, charm, bottom, and top. Each comes with its own mass and other defining properties. The lighter ones, especially up and down, are the most common ingredients in ordinary hadronic matter. Strange quarks appear in many important mesons and baryons as well, especially in particles that played such a large role in the strange years of the particle zoo. The heavier quarks, charm, bottom, and top, belong to a more energetic corner of the subatomic world. Some of them appear in short-lived particles created in high-energy collisions, and their study has told physicists a great deal about the workings of the standard model. But when we are talking about mesons in their most general and introductory sense, the central idea is this. A meson is built from one quark and one antiquark. That definition is elegant partly because it is minimal. 1 and 1. Not a larger assembly, not a 3-body structure like a baryon, but the smallest quark-based pairing that can form a meson. Even so, this smallest pairing is not small in the ordinary sense of being simple to picture. The quark and antiquark do not sit side by side like tiny billiard balls. They are bound by the strong interaction, described by quantum chromodynamics, and that interaction is unlike anything in ordinary life. You cannot sensibly imagine it as a little hook, or a spring, or a dab of cement between particles. The strong interaction is a field theory. It involves gluons, confinement, and a kind of internal activity that refuses to become a tidy household metaphor no matter how politely one asks. Still, before the binding becomes too complicated, it helps to pause over the antiquark itself. An antiquark is the antiparticle partner of a quark. For every quark flavour there is a corresponding antiquark flavour. An up quark has an up antiquark. A strange quark has a strange antiquark, and so on. The antiquark has the same mass as its corresponding quark, but opposite values for certain quantum properties, including electric charge and some conserved numbers. This does not mean an antiquark is somehow less real, or ghostly, or made of absence. It is a genuine particle. In many ways, the prefix anti causes more confusion than it helps for people hearing it casually. It sounds like the antiquark ought to be a negation rather than a presence. In physics, it is fully present. It just carries opposite quantum labels where the theory demands them. One of the most important lessons in particle physics is that opposites are not necessarily enemies. A quark and an antiquark can annihilate under the right circumstances, yes, but they can also bind into a meson. That is already a clue that the word pair in this setting should not be mistaken for a fragile temporary meeting. In mesons, the quark and antiquark are held together strongly enough to behave as a distinct particle with its own mass, spin, lifetime, and decay channels. The meson is not merely the sum of two names placed side by side. It is a bound state with its own physical identity. This is where the phrase smallest pairing becomes especially useful. Mesons are the lightest and most economical hadronic structures in terms of valence quark content. If you want a strongly interacting particle built from quarks without going to the 3-quark pattern of baryons, the quark-antiquark combination is the basic route. That is why mesons occupy such an important conceptual place. They are simple enough to serve as a first composite system in the strong interaction, but rich enough to display many of its most fascinating features. They are, in a sense, the first place where quarks show how much complication can emerge from very little. It is tempting to imagine that if mesons are made from only two valence constituents, they ought to be easier than baryons in every way. Sometimes they are easier to classify, and sometimes they are easier to approximate in theory. But the strong interaction has a way of denying complete simplicity to everyone involved. The quark and antiquark are embedded in gluon fields. Their momenta are not fixed in a classical way. Their effective behaviour depends on the energy scale at which the system is probed. Quantum fluctuations contribute additional temporary quark-antiquark pairs, often called the C. So even in the smallest pairing, the word only can be misleading. Only two valence constituents does not mean only two things are happening. Still, valence structure matters because it tells us what kind of meson we're dealing with. A pion, for instance, belongs to the lightest meson family and is built from combinations of up and down quarks and antiquarks. A kaon includes a strange quark or antiquark paired with an up or down partner. Heavier mesons can involve charm or bottom quarks. Each pairing leads to characteristic masses, lifetimes, and decay behaviour. In that sense, the Meson spectrum is like a language in which different quark pairings spell out different particles. The grammar is strict. You do not get arbitrary combinations producing arbitrary results. The allowed states reflect the underlying symmetries and interactions of the theory. If that sounds orderly, it is because this is one of the places where physics rewards patience with elegance. The quark model does not merely say that mesons are made from quark-antiquark pairs. It also explains why specific groupings occur, how they can be arranged into families, and why some mesons are lighter or more stable than others. Of course, stable here is always relative. Many mesons are short-lived by everyday standards to an almost comic degree. If a fruit fly had the lifespan of some mesons, it would write its memoirs in panic. But within the subatomic world, lifetimes vary in meaningful ways, and those variations tell us about the forces involved in production and decay. The lightest quarks deserve special attention because they show how subtle the word mass can be in this context. The up and down quarks have small masses compared with the masses of many hadrons made from them. This means that a large part of the mass of composite particles like protons, neutrons, and many mesons does not come simply from adding up constituent masses in the way one adds apples in a basket. Much of it arises from binding energy, motion, and the dynamics of the strong interaction. So when asking what a meson is really made of, one has to be careful not to reduce the answer to ingredients alone. The quark and antiquark are essential, but the energy bound up in their interaction is part of what the meson is. That becomes even clearer when one remembers that quarks are never found in isolation under normal conditions. This is confinement, one of the defining features of the strong interaction. You can produce quarks in high-energy processes, and you can probe their existence indirectly and decisively through scattering experiments and the behaviour of jets. But you do not pluck a single quark out of a meson and place it neatly on a tray. The force between colour-charged objects does not fade away in the simple manner of the electromagnetic force. Instead, trying to separate quarks tends to inject enough energy into the system that new quark-antiquark pairs can be created. Rather than producing a lone quark, the system reorganizes into new bound states. Nature, at least in this domain, has a marked preference for keeping colour confined. This means a meson is not just a partnership of convenience. It is one of the basic ways the theory allows quarks to appear in observable hadronic form. The quark and antiquark together can combine their colour charges into a colour-neutral state. That colour neutrality is crucial. A meson, like a baryon, must be colourless as an observed particle. Again, colourless here has nothing to do with sight. It means the internal colour charges combine in such a way that the meson as a whole carries no net colour charge. This is one of the deep consistency conditions of quantum chromodynamics. Hadrons are observed as colour-neutral bound states, even though their constituents are colour-charged. There is something both strict and generous about that rule. Strict because it sharply limits what can exist as an isolated hadron. Generous because within that restriction, an astonishing variety of particles can still arise. Different flavours, different spin alignments, different orbital arrangements, different energy levels. All of these contribute to a Meson spectrum that is surprisingly rich. The smallest pairing does not produce a small variety. It produces a wide family tree. Now, if one quark and one antiquark are enough to make a meson, the next sensible question is whether all mesons are equally simple in that sense. The answer is no, not really. There are mesons that fit beautifully into the conventional quark-antiquark model, and there are also hadronic states that may involve more elaborate structures. In modern experiments, some resonances appear difficult to describe as ordinary quark-antiquark mesons alone. They may contain 4 quarks in a more explicit sense, or involve significant gluonic excitation, or behave like loosely bound molecular arrangements of other hadrons. This is one of the reasons the old zoo spirit still lingers in modern hadron spectroscopy. Even after the quark model brought profound order, there remain corners where the strong interaction continues to produce states that test the boundaries of our categories. But the conventional meson remains the essential starting point, and it remains genuinely fundamental to understanding how the strong interaction organizes matter. A quark and an antiquark form the basic valence content. Around that content, everything else becomes possible. The meson can be light, like the pion, and play a crucial role in low-energy nuclear physics. It can carry strangeness, like a kaon, and reveal the peculiarities of weak decay and symmetry breaking. It can contain charm or bottom quarks, becoming a valuable laboratory for testing the standard model with precision. Each of these is still, at heart, a story about the smallest pairing and the different ways nature lets it play out. There is also a conceptual reason mesons are so useful when first learning quark physics. They force you to abandon the old intuition that a particle is always a single, indivisible object, while not yet requiring the full complexity of 3 valence quarks as in baryons. They sit in a middle place between the elementary and the composite, between the clean and the unruly. An electron, as far as we know, is elementary. A proton is composite, with 3 valence quarks and a busy internal sea. A meson says, in effect, let us practice thinking compositionally, but with the smallest non-trivial bound state available. That makes it an ideal conceptual training ground, though the meson itself may object to being treated like an educational stepping stone when it has so much character of its own. Another thing worth noticing is how much of meson identity depends on the relationship between the quark and antiquark, not just their individual names. Their spins can combine in different ways. Their relative motion can contribute angular momentum. The resulting meson can therefore have different overall quantum numbers, even when the flavor content is similar. This means 2 mesons may involve the same types of quark and antiquark but differ in mass and other properties, because the internal configuration is different. In everyday language, the ingredients can be the same while the state is not. Physics here behaves less like a pantry and more like music. The same instruments can produce different works depending on arrangement and motion. That point matters because it helps explain why Meson spectroscopy became such a rich field. Physicists are not merely cataloguing which quark flavors can pair. They are studying how those pairings can be excited, how they transform, how they decay, and what the full spectrum of allowed states reveals about the strong interaction itself. A meson is therefore both a particle and a probe. When you understand its structure, you're also learning about the force that binds it. When you measure its mass or lifetime or decay pattern, you are testing the theory that describes the deepest binding mechanism in ordinary matter. All of this brings us back to the deceptively plain question of what a meson is really made of. At one level, the answer remains satisfyingly crisp. A meson is made of a quark and an antiquark. That is the basic valence composition, the smallest pairing that defines the particle as a meson rather than a baryon or something else. But at another level, this pairing exists inside a system alive with gluons, fluctuations, internal motion and confinement. The quark and antiquark are the central actors, yet the stage matters so much that you cannot really describe the performance by naming the actors alone. Perhaps that is why mesons are so useful for learning how particle physics thinks. They teach you early that matter at very small scales is not built in the same conceptual style as furniture, buildings, or even atoms in the old textbook sense. It is built through field excitations, bound states, conservation laws, and interactions that do not resemble ordinary contact mechanics. A meson is not a little bag with two things inside it. It is a quantum state whose identity depends on the allowed pairing of quark and antiquark under the rules of the strong interaction, and once that much is in place, another part of the story starts asking for attention almost immediately. If quarks and antiquarks are the defining pair, what is actually holding them together so powerfully? What does the strong force do that makes this binding possible? And why is its behaviour so different from the forces we meet in everyday life? Because the more closely one looks at a meson, the more it becomes clear that the real drama is not only in the pair itself, but in the gluons and the binding they create between them. If quarks and antiquarks are the defining pair inside a meson, then the next question arrives almost immediately and refuses to sit quietly in the corner. What is actually holding them together? Not in the vague sense of attraction, and not in the comforting everyday sense of glue, string, magnetism, or pressure, but in the much more serious sense of what rule of nature makes a quark and an antiquark behave like a bound particle instead of simply parting ways. This is where the strong force enters properly, and once it does, the whole discussion becomes both clearer and stranger at the same time. Out of the known fundamental interactions in physics, the strong force is the one with the most dramatic relationship to matter at very small scales. Gravity dominates the motion of planets and galaxies. Electromagnetism shapes chemistry, light, atoms, and nearly everything you can touch. The weak interaction governs certain kinds of decay and transformation among particles, but the strong force is the one that grips quarks and keeps them confined inside hadrons. Without it, protons and neutrons would not exist as we know them. Atomic nuclei would not hold together in any familiar way. Stars would not build the elements in the same form. The material universe would be less a place and more a warning. The name strong force is not exaggerated. It is not a bit of scientific bravado or a marketing decision made by tired physicists in a hurry. It is called strong because at the scale relevant to quarks, it is indeed extraordinarily powerful. If you imagine the electric attraction between opposite charges, that is already a useful and deeply important force. But the strong interaction operates in a way that is more intense and much less polite. It does not simply pull particles together and then fade gently into the background as they settle into place. It defines the very possibility of certain particles existing at all. Now there is a useful distinction to make early, because the phrase strong force can refer to two closely related but not identical ideas depending on the context. At the deepest level, the strong interaction is the force between quarks and gluons, described by the theory called quantum chromodynamics. This is the fundamental interaction that acts on colour charge. At a more effective and slightly less microscopic level, one can also talk about the residual strong force, the interaction that acts between protons and neutrons inside atomic nuclei. That residual force is related to the deeper quark-level interaction, but it's not the same thing in direct form. In a way, it is like the difference between the chemistry inside a molecule and the way molecules stick to each other in larger structures. Related, yes, but not identical. For Mesons, we are interested in the more fundamental level. A meson is a quark and an antiquark bound together by the strong interaction, and the particles that carry that interaction are called gluons. The name gluon is simple enough that it can almost lull you into thinking the concept will be simple too. One hears gluon and imagines a tiny worker going about with a pot of adhesive, making sure the quarks do not drift apart. This is understandable, but it is not really how the theory works. A gluon is not a blob of sticky stuff. It is the quantum carrier of the strong interaction, a field excitation that mediates the force between colour-charged particles. That description already sounds suspiciously similar to what many people hear about photons in electromagnetism. Photons carry the electromagnetic interaction, gluons carry the strong interaction, so perhaps the story is just the same with more dramatic consequences. That is the point where particle physics smiles in a way that should make you slightly cautious. The analogy is useful for a moment, but only for a moment. Gluons and photons are alike, in the broad sense that both are force carriers in quantum field theories. Beyond that, their personalities diverge quite sharply. The crucial difference is that photons do not carry electric charge, while gluons do carry the strong interaction equivalent colour charge. That means gluons can interact not only with quarks, but with one another. This single fact is one of the reasons the strong interaction behaves so differently from electromagnetism. In the electromagnetic case, the field carrier does not itself act as a source of the same charge. In the strong case, the carriers participate in the interaction directly. The result is a theory with much richer self-interaction and much less intuitive behaviour. To understand why this matters, it helps to think in terms of how forces behave with distance. In electromagnetism, oppositely charged particles attract, and the force weakens as they move farther apart. This fits ordinary experience well enough. Magnets, charged objects, the way light spreads, all of it gives some sense that fields can extend outward and dilute with distance. The strong interaction does not behave that way between quarks. At very short distances, quarks can behave almost as though they are loosely interacting. This feature is called asymptotic freedom, and it was one of the great theoretical discoveries of 20th century physics. It means that when quarks are extremely close together, the strong force becomes weaker in a certain technical sense. But as you try to pull them apart, the interaction does not simply fade. It becomes stronger. This is one of the most unintuitive but central ideas in the whole subject. The farther apart you try to separate a quark and an antiquark, the more energy builds in the colour field between them. If you keep pulling, the system does not reward your effort with a lone quark at one end and a lone antiquark at the other. Instead, the stored energy becomes large enough to create a new quark-antiquark pair from the vacuum. The result is not isolation, but reorganization. You began by trying to separate one meson, and nature answered by making more hadrons. This is confinement, and it is one of the defining signatures of the strong interaction. There is something almost stubborn about confinement. It is as though the theory refuses to let colour-charged particles appear naked in the world. Observable particles must be colour-neutral. Mesons achieve that neutrality by combining a quark and an antiquark with opposite colour structure in the relevant sense. Baryons do it with 3 quarks. The details belong to group theory and the mathematical structure of quantum chromodynamics, but the broad physical result is clear. You do not observe free quarks under ordinary conditions, you observe bound states. The meson is one of the simplest and most important of those states. This makes the word bind especially significant. A gluon does not simply keep the quark and antiquark acquainted, It is part of a field structure that makes the Meson possible as a color-neutral object. The binding is not mechanical. It is not like tying two stones together with string. It is energetic and field-based. The quark and antiquark are immersed in a strong interaction environment in which gluon exchange and gluon self-interaction shape the allowed state. Their motion, confinement, and interaction energy all contribute to the mass and identity of the meson. It is also worth noticing that gluons themselves are massless in the theory, at least in the same broad sense that photons are, and yet the force they produce has a very short effective range in terms of observable consequences between hadrons. This seems paradoxical at first because one might expect a massless force carrier to produce a long-range force. The difference again comes from the nature of the theory. The self-interacting gluon field and the confinement of colour prevent the strong interaction from appearing in ordinary matter, the way electromagnetism does. We do not feel a large long-range colour force in the room, because colour-charged particles are locked inside colour-neutral hadrons. What leaks out at the hadronic level is the residual interaction that binds nuclei, not the full raw colour force between free quarks, because free quarks are not available to take part in everyday furniture. At this point, mesons start to look less like little particles in the old mechanical sense, and more like standing agreements enforced by the theory. A quark and an antiquark are allowed to exist together in a colour-neutral bound state. The gluon field makes that state energetically meaningful. The whole object is a composite particle, but not one assembled from static parts that remain unchanged. Inside a meson, the quark and antiquark are in constant quantum motion. Gluons are actively involved. Additional fleeting quark-antiquark pairs may contribute as part of the sea. The identity of the meson is stable enough to measure, but the internal picture is not one of stillness. This is one reason the phrase "the gluons that bind" is accurate, but only if bind is heard in the right way. In everyday speech, binding often means fixing something into a rigid arrangement so it stops changing. In particle physics, the opposite is closer to the truth. The binding in a meson is dynamic. It is not the absence of motion, but the rule that governs the motion. The quark and antiquark do not become inert because they are bound. They become a system whose properties emerge from the interaction itself. One useful way to think about this without becoming too decorative is to compare it to a musical note on a violin string, though only briefly and with some caution. The note is not a little object sitting in one place on the string. It is a pattern sustained by motion, tension, and boundary conditions. Change those, and the note changes. A meson is not like a note in every respect, of course, but the comparison helps with one important point. The identity of the thing comes from an allowed pattern under specific rules, not from a pile of tiny rigid pieces sitting quietly. In a meson, the allowed pattern is determined by quantum chromodynamics. The theory itself is demanding, and this is where many simplified explanations wisely lower their voice and step backward a little. Quantum chromodynamics is extraordinarily successful, but it is not always easy to solve in the regime where mesons live. When the strong interaction becomes very strong at low energies and larger hadronic scales, calculations become difficult. This is why particle physicists use a variety of tools, approximations, effective theories, and numerical methods such as lattice calculations to study mesons and hadrons in detail. The theory is known. The challenge is not ignorance of the rules, but the sheer richness of what those rules produce. That richness shows up in meson spectra. Different quark-antiquark combinations can form different mesons, but so can different internal arrangements of the same flavours. Spin matters, relative orbital motion matters, excited states matter. The gluon field contributes to how these states are structured and how their masses come out. So when physicists study mesons, they are not merely checking that quark plus antiquark equals particle. They are examining the consequences of strong binding in all its forms. A meson can be a ground state, an excited state, a short-lived resonance, or part of a decay chain that reveals something about the underlying force. In all of these, gluons are not background staff. They are central to the production. There is another subtlety that helps explain why mesons have been so important historically. Long before quantum chromodynamics had its modern form, mesons were already tied to the problem of nuclear forces. Pions in particular played a key role in describing the interaction between protons and neutrons. In the later quark picture, the pion is a quark-antiquark bound state, but it is also involved in the effective force between nucleons. This means mesons sit at an especially interesting bridge between deep theory and observable nuclear behaviour. They are products of the strong interaction at the quark level, and also participants in the residual effects of that interaction at larger scales. The pion has another special status as well. It is unusually light compared with many other hadrons, and this lightness is related to deep features of symmetry in quantum chromodynamics. Without drifting too far into formal territory, the pion is not just another meson. It reflects the way the theory behaves when certain approximate symmetries are present, and then broken in specific ways. This is a lovely reminder that even within the Meson family, not all members are equally ordinary. Some carry special theoretical significance because their properties reveal general features of the strong interaction itself. The same goes for heavier mesons. Charmonium, which involves a charm quark and a charm antiquark, and bottomonium, which involves the bottom versions, provide valuable laboratories because their heavier masses make some aspects of their internal dynamics more tractable theoretically. These systems are often compared, loosely and carefully, to atomic bound states because they can show a spectrum of excitations in a way that is especially instructive. But again, the comparison should not be taken too literally. The strong interaction is not electromagnetism with louder shoes. Even when analogies help organize the mind, the underlying physics remains its own thing. One reason people find gluons harder to visualize than photons is that photons at least have familiar consequences. Light is visible, radio waves are part of daily technology. Electromagnetism leaves clues all over ordinary life. Gluons do not offer that kind of hospitality. Their effects are mostly hidden inside hadrons and in the debris of high-energy collisions. We know them not because we can isolate and display them comfortably, but because the theory that includes them explains an enormous range of phenomena with extraordinary success. The structure of hadrons, the behaviour of jets in particle collisions, scaling violations in scattering experiments, the properties of quark-bound states, all of these point back to the gluonic structure of the strong interaction. So if you return to the meson and ask what is doing the actual holding together, the honest answer is that the strong interaction, mediated by gluons and governed by quantum chromodynamics, binds the quark and antiquark into a colour-neutral hadron. But this answer only sounds finished if one has not spent enough time looking at it. In practice, it opens the door to everything that makes hadron physics so rich. The interaction grows strong with separation. The field carriers interact with one another. Colour is confined. The mass of the composite system comes not just from constituent masses, but from energy and motion in the field. The interior is dynamic, not static. The Meson is a bound state because the theory allows and enforces it, not because the universe happened to misplace a microscopic bottle of glue. There is also a pleasing irony here. The strong force is responsible for some of the most stable structures in the material world, and yet at the level of many mesons it produces particles that are fleeting, short-lived, and eager to decay into other things. Stability in physics is always contextual. A force can be immensely binding without guaranteeing permanence for every state it creates. Some mesons are useful precisely because they do not last long. Their decays reveal the interplay between the strong interaction and other forces, especially the weak interaction. Their masses and branching patterns test the theory. Their production in collisions helps researchers study how quarks and gluons behave when energy is concentrated into tiny regions of space. So the gluons that bind do more than hold a meson together for a moment. They express one of the deepest rules in physics, that quarks are confined and hadrons are the observable language in which that confinement becomes visible. A meson is one of the clearest statements of that rule. It is a quark and an antiquark bound not by a quiet attraction, but by a powerful and dynamic field whose carriers interact, whose strength does not fade in the usual way, and whose consequences shape everything from the interior of matter to the outcome of particle collisions. And once that much is in place, another comparison starts to matter, because it is one thing to say that mesons and protons both belong to the family of hadrons, and both owe their existence to the strong interaction. It is another to ask why one is built from a quark and an antiquark while the other is built from 3 quarks, and how that difference changes everything from their structure to their role in the universe. At this point, it becomes useful to place the meson beside a proton and ask a very direct question. If both belong to the broader family of hadrons, if both owe their existence to the strong interaction, and if both are built from quarks, then what exactly makes them different? It is tempting to answer too quickly. One might say that a meson is a quark and an antiquark, while a proton is 3 quarks, and leave it there. That answer is correct, but only in the same way that saying a violin has strings while a piano has keys is correct. It identifies a central difference, but it does not yet explain why that difference matters so much for behavior, stability, role, and structure. The proton is one of the great long-term residents of the visible universe. It sits in the nucleus of every hydrogen atom, and in the nuclei of all heavier elements as well. It helps make stars possible, chemistry possible, planets possible, and the entire ordinary world possible. It is so familiar in modern science that it can seem almost modest, like reliable furniture that has always been there. The meson is very different. Mesons are real and important, but they are not the ordinary long-lived material of tables, oceans, skin, or stone. Most mesons are unstable. They appear in high-energy events, in nuclear interactions, in cosmic ray showers, in particle beams, and in the internal language of hadronic physics, but they do not build the enduring bulk of ordinary matter in the way protons do. That alone tells you the difference is not just counting quarks, it runs deeper into how these particles fit into the universe. Let us begin with the basic composition, because it remains the cleanest doorway into the subject. A proton is a baryon. In the quark model, baryons are built from 3 valence quarks. The proton specifically contains 2 up quarks and 1 down quark. A meson, by contrast, is built from 1 quark and 1 antiquark. This makes the meson the simplest quark-based pairing, and the proton a more complex 3-body-bound state. That difference in valence structure affects almost everything that follows, including electric charge possibilities, spin patterns, how the particles are grouped into families, and how they behave under the symmetries of the strong interaction. Charge is one of the easiest places to see the distinction in a concrete way. The proton carries a positive electric charge. This comes from the charges of its constituent quarks adding up in a particular way. Mesons can be positively charged, negatively charged, or neutral depending on which quark and antiquark they contain. So a proton has a fixed familiar charge, while the meson family includes a wider variety of charge arrangements. This does not by itself explain the full conceptual difference, but it shows that the meson family is broader in some respects, because the quark-antiquark combination can come in several forms. A more profound distinction lies in what is called baryon number. In particle physics, baryons and mesons belong to different classes, partly because they carry different values of this conserved quantity. Baryons such as the proton carry baryon number. Mesons do not. This may sound like a technical bookkeeping detail, but it is one of the reasons the proton belongs to a fundamentally different category from a meson, even though both are hadrons. The proton is not just a heavier or more durable cousin of the meson. It is a member of a separate hadronic class with its own conservation rules and its own role in the long-term accounting of matter. That role matters enormously. Protons are part of what is often called matter in the persistent everyday sense. Mesons are more often part of interactions, exchange processes, decay chains, and transient states. If you look at the visible matter around you, It is full of electrons, protons, and neutrons. It is not full of pions or kaons sitting quietly in the wallpaper. Mesons can certainly be produced in abundance in energetic environments, but they are usually temporary. This is not because the strong force failed to do its job for them. On the contrary, it bound them just fine. Their short lifetimes reflect the fact that once formed, many mesons can transform into other particles through allowed decay processes. The proton, by contrast, is extraordinarily stable. In the standard model, it has no easy decay route into lighter ordinary particles that preserves all the necessary conservation laws, so it endures. This brings us to one of the most useful conceptual differences. A proton is stable enough to be treated as a permanent building block of ordinary matter. A meson is usually better thought of as a state that occurs within the ongoing traffic of particle interactions. It can be created, measured, studied, and categorized, but it does not normally stick around to form the long-lived scaffolding of atoms. That makes mesons essential to physics, without making them central to the visible durability of matter. They are important not because they last, but because they reveal. Their internal dynamics also differ in instructive ways. Both protons and mesons are governed by the strong interaction, and both contain more than just their valence quarks when examined closely. In either case, there are gluons and a sea of transient quark-antiquark pairs contributing to the full quantum picture. But the valence structure still matters because it shapes the simplest identity of the bound state. A proton begins from 3 valence quarks held together in a colour-neutral arrangement. A meson begins from a quark and an antiquark in their own colour-neutral pairing. The mathematics of the strong interaction allows both kinds of colour-neutral state, but their structure is not interchangeable. The proton is not just a meson with an extra quark tossed in for sturdiness. It's a different kind of allowed bound state from the start. Spin gives another useful window into the distinction. The proton has spin 1/2 and is therefore a fermion. Mesons, built from a quark and an antiquark, are bosons. This has major consequences. Fermions and bosons obey different statistical rules. Fermions are subject to the exclusion principle, which is part of the reason ordinary matter has the structure it does. Electrons in atoms cannot all collapse into the same state. Protons and neutrons in nuclei also follow fermionic behaviour. Mesons do not. Their bosonic character places them in a different category of particle behaviour. This difference is not merely a taxonomic curiosity. It helps determine how these particles act collectively, how they are exchanged in interactions, and why protons and mesons occupy such different conceptual places in physics. The proton also has a special significance because it is the lightest baryon. That matters because if baryon number is conserved, heavier baryons can decay down toward lighter ones, but the proton has nowhere obvious to go. It is already at the bottom of its baryonic family in ordinary conditions. Mesons do not enjoy that same protected status because they are not baryons at all. Many of them can and do decay into lighter particles without violating the relevant conservation rules. So the proton is not simply more stable by accident. Its stability is deeply tied to its identity as the lightest baryon, and to the conservation laws that structure particle physics. This is one reason the proton feels almost foundational, while the meson feels more situational. The proton is a long-lived endpoint in one category of matter. Mesons are often intermediate expressions of another kind of organisation within the strong interaction. A pion can be produced in a collision and then decay. A kaon can reveal subtle features of weak interactions and symmetry violations before it vanishes. A heavier meson can serve as a precision laboratory for testing aspects of the standard model. These are valuable roles, but they are roles of activity rather than permanence. Another way to say it is that the proton stays and the meson speaks. The proton remains present in ordinary matter. The meson often appears to tell you something about the forces and processes at work, then leaves through decay. That is not a sentimental observation. It is a practical one. Particle physicists often learn from mesons by studying their production and decay patterns. while chemists and material scientists live mostly in a world organised around the enduring presence of protons, neutrons and electrons. There is also an important mass-related point. Although both protons and mesons owe much of their mass not merely to the bare masses of their quark constituents, but to the energy of the strong interaction, the details differ because the bound states differ. The proton is a 3-quark system with its own internal momentum distribution, gluon content and energy structure. A meson is a quark-antiquark system with a different arrangement and different available states. Even when quark masses are small, the resulting hadron masses can be substantial because binding energy and internal motion contribute so heavily. So the difference between proton and meson is not just in ingredients, but in the entire energetic architecture of the bound state. Historically, this difference also shaped the way the two kinds of particles were understood. Protons were known early as parts of atomic nuclei, and were woven into the structure of matter long before the quark model existed. Mesons arrived later as more puzzling, often unstable particles whose meaning had to be worked out through high energy and nuclear physics. The proton was familiar before it was deeply understood. Mesons were mysterious almost from the moment they were noticed. That history has left a mark on how people intuitively regard them. The proton feels like a resident. The meson feels like a visitor. In physics, of course, both are equally real, but their practical identities remain quite different. The proton also differs from a meson in the way it participates in the architecture of nuclei. Protons and neutrons are the nucleons. They form the dense core of atoms. The force between them inside nuclei is not the raw quark-level strong interaction in its direct form, but a residual effect of it. Mesons, especially pions, played an important historical role in describing that residual force. So there is a striking asymmetry here. The proton is one of the objects being bound inside the nucleus. The meson, in one effective description, helps account for the force between such objects. One becomes part of the enduring structure. The other helps describe the interaction that helps hold the structure together. This should not be taken too literally in the old mechanical sense, as though a meson is constantly flying back and forth inside every nucleus like a courier with a satchel. Modern theory is deeper and field-based, but the point remains useful. Protons and mesons are not merely different kinds of hadron sitting beside each other in a catalogue. They often occupy different jobs in physical explanations. The proton is a constituent of ordinary nuclei. The meson is often a probe, a mediator in effective theories, or a short-lived product of interaction. Even when one steps away from low-energy nuclear physics and into collider experiments, the difference remains sharp. A proton beam can be accelerated and smashed into targets or other beams, because protons are stable enough to make practical beams. Mesons are usually produced as part of the collision outcome. They then decay into other particles that detectors record. So once again, the proton acts like something you can use as infrastructure, while the meson acts like something you investigate as a consequence. One is a tool and a target. The other is more often a signal and a clue. There is a subtle conceptual point hidden in all this. Because the proton is stable and familiar, people sometimes imagine it must be simpler or more elementary than a meson. In fact, within the quark model, the proton is in one sense more structurally complicated because it has 3 valence quarks rather than 2. Its apparent simplicity comes not from being more elementary, but from being more durable and more central to ordinary matter. Familiarity is not the same as simplicity. The meson may have fewer valence constituents and still feel more exotic because it is not part of the quiet furniture of the world. The antiquark is especially important here. A meson contains an antiquark, a proton does not. That single fact carries a lot of weight. The presence of an antiquark in the meson means that mesons naturally sit closer to the world of particle and antiparticle pairings, annihilation possibilities, and transient high-energy production. A proton, being a baryon made of 3 quarks, belongs squarely to the side of long-lived matter, as we usually encounter it. This does not mean mesons are somehow less matter, or less real. it means their composition places them differently within the map of particle processes. If one looks even more closely, the distinction between proton and meson also affects the kinds of states that can exist. In mesons, the quark and antiquark can combine their spins and relative orbital motion into a wide range of bosonic states. In baryons like the proton, the three quarks must be arranged in ways consistent with fermionic statistics and color neutrality, leading to a different spectrum of possible excitations. Both families have excited states and resonances, but the internal combinatorics and symmetry constraints differ. That is why Meson spectroscopy and baryon spectroscopy, while related, are not simply the same exercise done with different particle names. There is also a pedagogical reason this comparison matters so much. Students first encountering the quark model often assume that once you know quarks are the ingredients, all hadrons are basically the same sort of object with different counts. But the strong interaction does not just count constituents. It organizes distinct classes of bound states with distinct behavior. Mesons are bosonic quark-antiquark states. Baryons are fermionic three-quark states. That difference changes their charge possibilities, statistics, role in matter, typical stability, and the kinds of conservation laws that frame them. The proton is not just another hadron. It is a very particular kind of hadron with exceptional importance. This also helps explain why the proton became such a central reference point in physics. It is not merely because it was discovered early, or because it is positively charged and convenient to draw in textbooks. It is because the proton sits at a rare crossing of properties. It is composite but stable. It is strongly interacting but present in ordinary matter. It is not elementary, yet it functions as a durable constituent of atoms. Mesons do not occupy that same crossing. They are composite and strongly interacting too, but usually unstable and more dependent on energetic environments for their appearance. In a way, the proton is a long sentence in the language of quarks that nature keeps reusing, while the meson is often a shorter phrase spoken in passing during interactions. Both are meaningful, both obey the grammar of the strong force, but they serve different purposes in the larger discourse of matter. And there is one final point worth lingering over because it brings us back to the original question of what a meson is really made of. If you ask what makes a meson different from a proton, the answer is not just that one has an antiquark and the other does not. It is that the meson and the proton represent two different solutions to the problem of how quarks can exist in observable color-neutral form. The strong interaction does not permit free quarks to roam about under ordinary conditions. Instead, it allows bound states. One major class is the baryons, including the proton. Another major class is the mesons. These are not variations on a single generic object. They are distinct kinds of hadronic existence, each shaped by the demands of color neutrality, the possibilities of quark content, and the rules of quantum statistics. So when placed beside each other, the meson and the proton reveal something fundamental. The strong interaction does not merely glue quarks into one standard package. It permits multiple architectures, and those architectures matter. The proton becomes part of the enduring structure of matter. The meson becomes one of the most useful windows into how quarks, antiquarks, and gluons behave when energy and interaction are allowed to speak more directly. And once that contrast is clear, the meson family itself becomes much easier to appreciate, because not all mesons are alike either. Some are light and central to nuclear physics, some carry strangeness, some include heavier quarks, and together they form a family whose variety tells us just how much can emerge from that smallest quark-antiquark pairing. Once the basic difference between mesons and protons is clear, the next sensible step is to look inside the meson family itself, because mesons are not one single particle repeated with minor costume changes. They are a wide and varied group. Some are light, some are heavy, some are charged, some are neutral. Some live long enough by particle standards to travel measurable distances before decaying, and some vanish almost as soon as they are formed. if the proton feels like a steady member of the household, mesons are more like a large extended family of relatives who all resemble each other in certain ways but behave very differently once they arrive. The two branches people usually meet first are the peons and the kaons. That is not only because they are historically important, but because they teach some of the essential lessons about how mesons are organised. They show how quark flavour changes the identity of a particle, how mass differences matter, how decay behaviour can reveal the force involved, and how a family tree in particle physics is never just about naming things. It is about seeing which properties travel together and which do not. Peons are the lightest mesons in the usual story, and that makes them especially important. There are three common peon states, one positively charged, one negatively charged, and one neutral. Their valence quark content involves only the light up and down quarks and their antiquarks. In a very rough sense, the charged peons are made from one up or down type quark paired with the opposite antiquark type, while the neutral peon is a mixture built from the corresponding light quark and antiquark combinations. That sounds simple enough, but the reason peons matter so much is not only that they are light, it is that they sit very close to some deep features of the strong interaction itself. Because the up and down quarks are relatively light, and because the strong interaction has certain approximate symmetries, when those quark masses are small, the peons emerge as unusually light mesons compared with many other hadrons. This is one of those cases where a particle is not merely another example in the catalogue, it is also a clue about the underlying theory. The peon helps reveal how symmetry works in quantum chromodynamics, and how that symmetry is not exact in the way the real world behaves. One can spend a very long and satisfying career learning just how much is hidden inside that sentence. Long before the full quark theory of hadrons was established, peons were already central to nuclear physics, because they helped explain the residual force between protons and neutrons in atomic nuclei. This gave them an importance beyond their own identity. They were not only particles to be discovered and classified, they were also part of the explanation for why nuclei hold together. Later, when the quark model and quantum chromodynamics brought a deeper description, the peon did not lose that significance. It simply became part of a larger and more accurate picture. That is often how physics matures. The old idea does not always collapse. It becomes the effective version of a deeper one. Kaons belong to the next notable branch in the Meson family tree, and they bring with them one of the most memorable ideas in particle physics, strangeness. A kaon contains one strange quark, or one strange antiquark paired with an up or down partner. That single change in quark flavour has major consequences. Kaons are heavier than pions because the strange quark is heavier than the up and down quarks. They also behave differently in production and decay, and historically they were among the particles that forced physicists to take the growing hadron spectrum seriously as something structured rather than random. The strange particles were puzzling because they were often produced through strong interactions, which meant they could appear readily in energetic collisions, but they decayed more slowly than one would expect if the same strong interaction were responsible for their disappearance. This mismatch led to the introduction of strangeness as a quantum number that was conserved in strong processes but not in weak ones. Kaons became some of the clearest examples of this pattern. In plain terms, they were easy enough to make in the right circumstances, but they did not vanish by the fastest route available to strong decays because the relevant conservation rules blocked that path. Nature was not being inconsistent. It was revealing that not all interactions obey the same detailed accounting. That made kaons historically important in more than one way. They helped establish the value of quark flavour as a real organising principle, and they also became crucial in the study of weak interactions and symmetry breaking. Even in a chapter focused mainly on Meson families, it is hard to avoid noting that kaons later played a starring role in one of the most famous discoveries in 20th century particle physics, the observation that certain symmetries involving matter and antimatter are not exact in weak decays. That is a bigger topic than we need right now, but it is worth noticing how often mesons, especially kaons, end up at the centre of important conceptual turns. For particles that do not build the walls of houses or the cores of atoms directly, they have had a very productive habit of exposing the weaknesses in human assumptions. If pions and kaons are the branches that most people first learn by name, the wider family tree extends much further. There are mesons built from charm quarks and their partners, mesons built from bottom quarks and their partners, and mixed flavour mesons involving one heavy quark and one lighter quark. Each group tells its own story. The light mesons, especially those made from up, down and strange quarks, are deeply tied to low-energy, strong interaction physics and the effective behaviour of hadrons. The heavier mesons are especially useful for precision tests because their larger masses and more distinct scales can make some aspects of theory cleaner to handle. Charmonium is one important example. This is the family of mesons built from a charm quark and a charm antiquark. Because both constituents are relatively heavy compared with the light quarks, the system has a somewhat different character from a pion or kaon. It still belongs fully to the world of quantum chromodynamics, but its spectrum of excited states can be studied in ways that feel a little more controlled. The most famous charmonium state was a major discovery because it provided powerful confirmation that the charm quark was not just a speculative idea. Once charmonium appeared clearly in experiments, the quark model gained a great deal of credibility. The family tree had acquired a branch that looked exactly like the theory had hoped it would. Bottomonium, built from a bottom quark and a bottom antiquark, plays a similar role for the bottom flavour. Again, this is a heavy quark pair forming a meson family with several possible states. These systems are often studied because they provide a relatively clean way to test predictions of the strong interaction in the heavy quark regime. They are not simple in the ordinary sense, but they can be simpler to approximate than the light mesons, where the full non-perturbative strength of the strong interaction becomes especially awkward. In other words, if the light mesons are a busy town square full of motion and chatter, some of the heavy quark mesons are more like a formal meeting where the participants still argue, but at least stay in their assigned seats long enough for the minutes to be taken. Then there are the open charm and open bottom mesons, where a heavy quark is paired not with its own antiquark but with a lighter partner. These mesons are especially valuable because they let physicists study the interplay between a heavy constituent and the lighter quark environment around it. In such systems, the heavy quark can act almost like an anchor around which the lighter degrees of freedom arrange themselves. This has inspired useful approximations and effective theories that help simplify certain aspects of the problem. The language may sound technical, but the basic idea is clear enough. Sometimes one very heavy constituent changes the character of the whole bound state in a way that makes certain patterns easier to see. What makes this a family tree rather than just a list is that the mesons are related through shared structure. They are all quark-antiquark bound states in the conventional picture, but their differences arise from the specific quark flavours involved, from how the quark and antiquark spins combine, from whether the pair carries orbital motion relative to one another, and from whether the state is in its lowest energy configuration or an excited one. This means the family tree is not arranged only by which quarks are present. It is also arranged by how the bound state is configured. That point is essential because even within one flavour combination, there can be several mesons with different masses and different quantum properties. The same basic pair of quark flavours can produce a ground state and a sequence of excited states. Their total spin can differ, their parity can differ, their internal angular momentum can differ. The result is not one particle per flavour pair, but a whole spectrum. This is why meson spectroscopy became such a rich subject. It is not enough to know the names of the ingredients. One has to know the allowed states of the composite system. In practice, physicists organise mesons into multiplars and families according to these shared properties. The light pseudoscalar mesons, which include the pions and kaons, form one especially important group. There are also vector mesons, scalar mesons, tensor mesons, and other categories corresponding to different internal quantum arrangements. These labels can sound intimidating at first. but they are really just ways of saying that the same quark-antiquark idea can be realised in different modes. A meson is not simply a pair, it is a pair in a specific state. There is also a useful historical lesson in how the family tree was uncovered. Physicists did not begin with a neat chart and then go out looking for confirmation. They found particles, often under difficult conditions, and gradually noticed regularities. The family tree was reconstructed from evidence. Pions stood out because of their role in nuclear interactions and their light mass. Kaons stood out because of their strange behaviour. Heavier mesons arrived through accelerator experiments and precision measurements. Each new branch strengthened the sense that hadrons were not arbitrary, but structured. Once the quark model took hold, the family tree became much more intelligible, though never completely tame. The untamed part remains important. Not every meson-like state fits comfortably into the simplest conventional scheme. Over the years, experiments have found resonances that look as though they may involve more than a simple quark-antiquark valence picture. Some candidates may be tetraquark states, some may be hadronic molecules, meaning relatively loose associations of two hadrons. Some may involve stronger contributions from gluonic excitation than ordinary mesons do. This does not ruin the family tree. It complicates the branches in interesting ways. The conventional meson picture remains central and successful, but the outer edges of hadron spectroscopy still allow nature to be inventive. Even so, for the main trunk of the tree, pions and kaons are still the best place to begin because they teach the right habits of thought. The pion shows that the lightest mesons are deeply tied to approximate symmetries of the strong interaction and to the effective forces within nuclei. The kaon shows that adding a strange quark changes the story enough to reveal new conservation rules and new decay behaviour. Once those two ideas are in place, the heavier branches become easier to understand. Change the quark flavour and you change the meson mass, the available decay paths, and often the theoretical tools best suited to describing the state. It is also worth emphasising that meson families are not simply theoretical inventions, placed on top of data for aesthetic reasons. Their structure shows up in measurable properties. Masses group in patterns. Decays follow predictable routes. Production rates depend on the quark content and the interaction involved. Lifetimes differ in ways the theory can often explain. Spectra of excited states line up with the expected internal arrangements. This is what gives the family tree its scientific weight. It is not a decorative chart. It is a compact way of representing how the strong interaction organises a wide range of observed particles. The neutral members of the family often deserve special attention because they can be more subtle than their charged relatives. Neutral pions, for example, have particularly rapid decay modes involving photons. Neutral kaons have a famously rich and delicate behaviour because they can mix with their antiparticle partners in ways that make their time evolution and decay patterns very instructive. This is another reminder that electric charge is only one visible part of meson identity. Two mesons may both be neutral and still differ enormously in what they are made of and how they behave. The family tree metaphor also helps with a practical point about naming. Particle names can feel arbitrary until you understand that they often point either to the quark content, the spin and parity class, the historical order of discovery, or the region of the spectrum in which the particle lives. Once you learn the broad categories, the names become less like random labels and more like surnames in a large but organised clan. That does not mean particle naming is always graceful. Physics, like any old institution, has accumulated some habits that made more sense to the people who were there at the time. Still, the family resemblance becomes much clearer once the quark model is in view. There is something else pions and kaons teach especially well. They show that being made of quarks does not mean being equally heavy, equally stable, or equally easy to produce. The choice of quark flavour matters because the quark masses differ, and because the conservation rules affecting creation and decay differ as well. A pion made only from the lightest quarks is a very different object from a meson involving charm or bottom. A kaon, with its strange component, already sits in a middle place where the light quark world meets a distinctly heavier flavour and a new set of weak decay patterns. In that sense, kaons are wonderfully educational particles. They are familiar enough to belong near the start of the Meson story, but rich enough to foreshadow much of what comes later. And this is really the deeper point of the family tree. It is not only a classification tool, it is a map of how complexity emerges from a very limited set of ingredients. 6 quark flavours do not sound like much. Yet from quark-antiquark pairings alone, with different internal states and interaction dynamics, nature builds an entire forest of mesons. Some are central to nuclear physics, some are precision tools for testing the standard model, some are clues about new forms of hadronic organisation. The variety is not accidental, it is what happens when a simple underlying rule is allowed to operate in a rich dynamical theory. So when you look at pions and kaons, you are not merely looking at 2 named particles, you are looking at the first clear branches of a much larger meson genealogy. Pions tell you what the lightest meson sector looks like when only the lightest quarks are involved. Kaons show what changes when strangeness enters the picture. Heavier families then continue the pattern into charm and bottom, while excited states and more unusual resonances keep the story from ever becoming too comfortable. That last point matters because a family tree is useful only if it helps you see both order and variation. Mesons share a common identity as quark-antiquark bound states, but they are not interchangeable examples of the same thing. Their masses, lifetimes, decays, and theoretical significance differ enough that each branch teaches a different lesson. And once that variety is in view, another question starts to press forward. If one meson can be light in symmetry linked like a pion, another strange and historically troublesome like a kaon, and another heavy and spectroscopically rich like charmonium, then what is actually happening inside the meson itself beyond the simple valence picture? Because a family tree tells you who is related to whom, but it does not yet tell you how the interior of each member is really put together from motion, gluons, and the ever-present quantum sea. Once the Meson family tree is in view, the next question becomes harder in a useful way. It is one thing to say that a pion is a quark and an antiquark, and that a kaon is a strange quark or strange antiquark paired with a lighter partner. It is another thing to ask what that actually means inside the particle itself. When physicists say a meson is made of a quark and an antiquark, they are giving the clean version first. It is the right place to start, but it is not the whole interior story. Inside a meson there is more than identity. There is motion, field energy, gluonic activity, and a constant background of temporary quark-antiquark pairs that appear and disappear as part of the quantum behaviour of the strong interaction. So the inside of a meson is not quiet. It is not empty space with 2 tiny objects sitting at opposite ends, like passengers on a very small bench. It is a dynamic bound state, and the more closely one looks, the less the old image of matter as fixed little pieces continues to help. The first important distinction is between valence quarks and C-quarks. The valence quarks are the ones that define the main identity of the meson. In a conventional meson, that means 1 quark and 1 antiquark. If you want to know why a positively charged pion is the particle it is, you look to its valence content. If you want to know why a kaon carries strangeness, again you look first to the valence content. These are the principal constituents in the bookkeeping sense. They are the reason the meson belongs to one part of the family tree rather than another. But that does not mean the rest of the interior is empty or irrelevant. The C-quarks are the additional quark-antiquark pairs that can appear transiently, because the gluon field inside the meson is active. Gluons can produce quark-antiquark pairs, and those pairs can contribute to the internal structure for a short time before the system reshuffles itself again. These C-quarks do not usually determine the main label of the meson in the way the valence pair does, but they are part of the full physical reality of the bound state. If you probe a meson at different energy scales, the importance of these contributions can shift. So a meson is not merely its valence pair, It is a quark-antiquark core embedded in strong interaction activity. This is one of the places where the word made becomes slippery. In ordinary life, if something is made of wood, there is not usually a hidden froth of temporary chairs inside the chair, appearing and disappearing while you make tea. At the quantum level, things are not so polite. A meson is defined by its valence content, but it is physically realized through a constantly active field structure. So when physicists ask what is inside a meson, they're not looking for a tiny inventory shelf with neatly labelled compartments. They're asking how the whole quantum state is organised. The gluons are central to that organisation. They carry the strong interaction, and because they themselves participate in the colour dynamics, they do much more than simply hold the valence pair together from a respectful distance. They contribute to the energy, the momentum distribution, and the internal activity of the particle. In some sense, a meson is as much a story about gluons as it is about quarks. The quark and antiquark give the meson its basic identity, but the gluon field makes that identity into a living bound state rather than a static definition. Motion matters immediately here, because quarks inside a meson are not sitting still. They are confined, yes, but confinement is not the same as rest. In fact, part of what gives hadrons their mass is the kinetic and interaction energy associated with the internal motion and field dynamics. So if you imagine shrinking the system down and finding two little particles parked quietly in place, you would miss most of what makes the meson a meson. The quark and antiquark are in motion. Their momenta are distributed according to the quantum state, and that motion is inseparable from the binding. A bound particle in quantum chromodynamics is not a still life. It is an allowed pattern of activity under very strict rules. This is one reason the idea of a wave function, or more broadly a quantum state, is so important. The meson is not described by exact little trajectories in the classical sense. You do not track the quark going here at this moment and the antiquark going there at that moment, in the way you might track two planets in a simple diagram. What you have instead is a probability-based description of the allowed state, including the distribution of momentum, position in a quantum sense, spin arrangement, and the contribution of additional degrees of freedom. The meson is not mysterious because physicists know nothing about it. It is subtle because the best available description is quantum from the beginning. That means one should be careful with pictures. Introductory explanations often use a simple image of a quark and an antiquark connected by a kind of strong interaction line, and that is perfectly fine as a starting point. It tells the truth at low resolution. But once the question becomes what is really going on inside, the answer must become more honest. The inside of a meson is a fluctuating quantum system in which the valence quark and antiquark are always central, while gluons and C-quarks contribute as part of the full-bound state. There is no silent interior waiting to be filled with intuitive furniture. Another important point is that momentum inside the meson is shared. The total momentum of the meson as a whole can be measured if the meson is moving, but internally that momentum is not carried entirely by the valence quarks. Gluons carry part of it, C-quarks can carry part of it. The exact distribution depends on the type of meson, and on the energy scale at which you probe it. This is one of those features that tends to surprise people when they first meet the modern picture. It feels natural to imagine that if a meson is made from one quark and one antiquark, then those two must carry all of the interesting internal content. In reality, the momentum structure is more democratic and more complicated. The strong interaction makes sure of that. This matters because it changes how one thinks about the mass of the meson as well. For the light mesons especially, the masses of the bare quarks are only part of the story, and often not the largest part. Much of the mass comes from the energy bound up in motion and interaction. So if you ask what a pion is made of, the valence answer is light quarks. But the mass of the pion is not just a matter of adding up the tiny masses of those quarks, like shopping items on a receipt. It reflects the whole bound state. In a hadron, energy and matter are tied together in a way that makes the interior much more than a list of ingredients. The sea quarks deserve a little more patience because their name can make them sound secondary, like background extras who wander through the scene holding coffee cups. That is not really fair. They may not define the name of the Meson, but they are part of the physical content that experiments and theory both have to reckon with. In many cases, the sea is essential to understanding measurable properties. It contributes to internal distributions, form factors, and the behaviour of the particle under different kinds of probes. The word sea was chosen because these pairs are numerous and constantly active, not because they are unimportant. If anything, the name reminds you that the valence pair is not floating in emptiness, it is immersed. This is a good place to notice how much the strong interaction resists the ordinary idea of a cleanly separable object. In chemistry, one can often isolate a molecule and meaningfully talk about the atoms within it as constituents with fairly stable identities. In a meson, the constituents are real, but they are so deeply embedded in the dynamics that the identity of the whole state cannot be reduced to a simple inventory. The quark and antiquark are not detachable beads, they are constituents in a bound quantum system shaped by confinement. The sea quarks are not separate additions from outside. They arise from the field activity within the system itself. Even the vacuum around the meson is not empty in the old sense. The theory allows fluctuations, and those fluctuations matter. There is also a difference between light mesons and heavy mesons that becomes especially interesting once one starts thinking about the inside. In mesons built from very light quarks, the internal motion is highly relativistic. The quarks move in a way that is deeply entangled with the full non-perturbative strength of the strong interaction. This makes the interior especially difficult to describe in simple terms. In heavy quark mesons, such as those involving charm or bottom, the picture can become somewhat more manageable in certain approximations because the heavy quark mass introduces a clearer scale. That does not make the system simple, but it can make some aspects of the motion easier to model. So even the phrase inside a meson does not refer to one identical kind of interior across the whole family. Different branches of the family tree bring different internal styles. In a light meson like a pion, the valence quarks are relatively light, and the contribution of the surrounding gluon field and quantum activity is especially important. The pion is also unusual because of its special connection to symmetry and quantum chromodynamics. That means it is not just a small light meson with a conventional interior, it reflects deeper features of the theory itself. In heavier mesons, the quark and antiquark can in some cases be treated more like a tightly bound heavy pair, moving in an effective potential, though even there one must be careful not to push the analogy too far. Particle physics is generous with approximations and merciless with those who mistake them for the final truth. The motion inside a meson also includes spin and angular momentum. The quark and antiquark each carry spin, and their spins can combine in different ways. In addition, their relative motion can contribute orbital angular momentum. These combinations help determine what kind of meson state you have. That means the interior is not only about which flavours are present, but also about how those constituents are arranged dynamically. Two mesons may contain the same quark flavours and yet differ because the internal state is different. The same cast can perform a very different play depending on direction and staging. This is why Meson spectroscopy matters so much. Physicists do not merely ask which quark flavours appear in a meson. They ask what internal state the bound pair occupies, how the gluon field contributes, how excited states differ from ground states, and how all of that shows up in measurable masses and decay patterns. The Meson is a laboratory for learning how quantum chromodynamics organises bound states, and the details of the interior are not decorative, they are the main point. It is also worth saying clearly that inside does not mean inside in the everyday geometric sense. A meson is not a hard shell with contents rattling around. When physicists talk about internal structure, they mean the degrees of freedom that make up the bound state and the distributions associated with them. The meson has a size in the sense that certain measurements can probe its spatial extent and internal distributions, But this is not the same as the size of a football or a spoon or even an atom as imagined in school diagrams. The interior of a hadron is not a little room. It is a quantum pattern. That may sound abstract, but experiments really do access parts of this story. High-energy scattering processes can probe how momentum is distributed among quarks and gluons. Decay rates and transition probabilities reveal information about internal structure and wave function overlap. Lattice calculations attempt to compute hadron properties directly from the theory on a discretized space and time grid. Effective theories help isolate the most important degrees of freedom in different energy regimes. So when physicists speak about valence quarks, C-quarks, and motion, they are not improvising poetic images for lack of data. They are using concepts grounded in measurable consequences. There is a quiet irony here. The closer physics gets to the interior of a meson, the less the notion of a tidy interior survives, and yet the more precise the science becomes. Precision does not always mean a simpler picture. Sometimes it means a more honest one. The old cartoon of two particles tied together is simple and useful. The fuller account, involving valence structure, C contributions, gluons, shared momentum, and quantum motion, is more complicated, but it is also more accurate. And accuracy is often what makes the world interesting in the first place. One can also see why mesons are such good teaching particles for the strong interaction. They are simpler in valence content than baryons, since they involve one quark and one antiquark rather than three quarks. Yet they already contain the full lesson that hadrons are dynamic systems, not mere assemblies. If even the smallest conventional quark-bound state already has a busy gluon field, temporary C-quarks, and non-trivial internal motion, then the naive picture of matter as a stack of tiny marbles has clearly run out of road. At the same time, the valence idea remains valuable. It gives the Meson its primary label and helps one make sense of the family tree. Without valence quarks, the whole classification would lose its backbone. So the right way to think about the interior is not to discard the valence picture, but to place it inside a richer framework. The valence pair tells you what kind of meson you're dealing with. The gluons and C tell you how the full quantum state lives. The motion tells you that the state is active rather than static. All three are necessary if the question is what is really inside. This is also why the Meson can be both conceptually simple and physically deep. The simple statement is one quark and one antiquark. The deeper statement is a bound quantum state whose defining pair exists amid gluonic dynamics, transient quark-antiquark C contributions, and continuous internal motion shaped by confinement. Both statements are true. The difference is not between right and wrong. It is between first contact and full conversation. And once the inside of the Meson is understood this way, another feature of mesons becomes much easier to appreciate. They are not durable objects in the ordinary sense. Many of them appear and then transform into something else very quickly. That transformation is not a side issue. It is one of the most revealing things about them. Because a meson is not only defined by what is inside at a given moment, but also by how that internal state can rearrange, convert, and vanish into other particles according to the allowed rules of the forces involved. Once the inside of a meson stops looking like a quiet little container and starts looking more like an active bound state, the next part of the story becomes much easier to understand. Mesons do not merely exist in a static sense. They are produced in interactions, they change through decay, and many of them disappear almost as soon as they have formed. That can make them sound fragile or accidental, but that is not really the right way to think about them. A meson appears when the underlying rules of the strong interaction allow energy and quark content to organize themselves into a quark-antiquark bound state. It transforms when that state can convert into other particles through one of the fundamental interactions. It vanishes, in the practical sense, when detectors no longer see the original bound state but only its products. So the life of a meson is not a strange interruption in physics. It is physics behaving exactly as it should in a world where energy can become matter. where bound states can form and where unstable configurations are allowed to turn into more stable ones. This is one of the most important differences between mesons and the ordinary matter people are used to imagining. A proton sitting in a hydrogen atom does not feel temporary in any human sense. It is there, and barring some truly extraordinary circumstance, it stays there. A meson is often much more event-like. It belongs naturally to the traffic of particle interactions. It is born in collisions, decays into other particles, or serves as part of the description of what happened in a strongly interacting system. That does not make it less real than a proton. It simply means its reality is often expressed through change rather than permanence. If the proton is part of the stable furniture of matter, the meson is part of the ongoing conversation between fields and particles. The first part of that conversation is appearance. Why do mesons appear at all? The short answer is that energy, when concentrated in the right way, can produce quark-antiquark pairs, and the strong interaction strongly prefers those pairs to show up as colour-neutral bound states, rather than as isolated quarks. This is already a consequence of confinement. If enough energy is available in a collision, nature can create quarks and antiquarks, but they do not remain free under ordinary conditions. They reorganize into hadrons. Mesons are among the simplest such hadrons, so they appear readily in energetic processes. Imagine two protons colliding at high speed inside an accelerator. From a distance, that sounds almost quaint, as though two very tiny beads are bumping into each other like impatient shoppers with small carts. In reality, the event is far more violent and much less bead-like. The protons are composite objects full of quarks, antiquarks, and gluons. When they collide at high energies, it is really their internal constituents interacting. Energy is concentrated into a tiny region. New quark-antiquark pairs can be created. Gluons can radiate and split. The result is not just a neat bounce, it is a shower of hadronic outcomes, and among those outcomes mesons are common. They also appear in other environments. Cosmic rays striking the atmosphere produce mesons. High-energy photons interacting with matter can help produce mesons. Unstable hadrons can decay into mesons as intermediate or final products. Even in nuclear processes at lower energies, meson exchange concepts can provide useful effective descriptions of interactions. So mesons are not confined to one special kind of laboratory event. They are part of the general repertoire of high energy and nuclear physics, because the strong interaction naturally gives rise to them whenever the conditions allow. Still, appearance is not random. Mesons do not simply pop out because the universe enjoys variety. Their production is constrained by conservation laws. Energy and momentum must be conserved. Electric charge must be conserved. Other quantum properties must be respected according to the interaction involved. If a particular meson is heavy, there must be enough available energy to create it. If it contains a strange quark, charm quark or bottom quark, the process must be able to produce that flavor content. That is why heavier mesons are generally associated with more energetic collisions. A pion is relatively easy to produce because it is light. A meson involving a bottom quark asks more of the event, rather like a houseguest who arrives with several trunks and a piano. This brings up an important distinction between production through the strong interaction and transformation through decay. The strong interaction is extremely effective at producing hadrons when energy is available, but once a meson exists, the way it disappears depends on which decay channels are allowed and which interaction is responsible for the change. Some mesons decay through the strong interaction and therefore do so very quickly. Others cannot use a strong decay route because of conservation constraints or because there is no energetically accessible strong channel available. In those cases, they may decay electromagnetically or through the weak interaction, and their lifetimes can be longer by particle standards. Longer here does not necessarily mean leisurely. In the meson world, even a relatively long life can still be absurdly brief by the standards of tea cooling or buses being late. The word vanish is useful, but it can also be misleading if heard too literally. A meson does not vanish into nothing. It decays into other particles, The original bound state ceases to exist as that particular quark-antiquark configuration, but its energy, momentum, and conserved quantum properties are carried forward by the decay products. This is one of the reasons particle detectors can study mesons at all. Many mesons are identified not by watching the meson itself sit around for any appreciable time, but by reconstructing the traces of what it decayed into. In particle physics, disappearance is often a matter of transformation, not erasure. Take the neutral pion as an example. It is one of the most short-lived mesons commonly discussed, and it decays rapidly into photons. Those photons then travel outward and can be detected in electromagnetic calorimeters. So the neutral pion appears in the data not as a lingering object but as a reconstructible event. Physicists infer its prior existence from the energies and directions of the photons. The meson has vanished in the practical sense that it is no longer there as a meson, but it has left a measurable signature. In that way, mesons are rather considerate. They may not stay long, but many of them leave clear forwarding information. Charged pions behave differently. They are longer lived than neutral pions and often decay into muons and neutrinos. That decay proceeds through the weak interaction. So already, within the lightest meson family, one sees that different members can transform in different ways and on different timescales. The neutral pion uses a rapid electromagnetic route. Charged pions often use a weaker and slower route. This is not inconsistency. It is a consequence of the available decay channels and the properties of the particles involved. Once again, the meson family is varied enough that one should be wary of assuming all members behave by one simple rule. Kaons are even more instructive because they reveal how a meson can appear through one interaction and vanish through another. A kaon can be produced readily enough in strong processes where strangeness is conserved overall, but it often decays through the weak interaction because its strange content cannot simply disappear through a strong decay route without violating the relevant constraints. This gives kaons lifetimes that are longer than one might expect for strongly produced particles, and historically, that was one of the clues that led physicists toward the concept of strangeness in the first place. Kaons were not breaking the rules. They were pointing to rules people had not yet written down properly. This difference between the production mechanism and the decay mechanism is one of the most useful habits of thought in particle physics. A meson is produced according to what is allowed in the initial interaction. It decays according to what final states are available and which forces can mediate the change. The fastest allowed route usually dominates. If the strong interaction can do it, the decay is typically very fast. If only electromagnetic or weak routes are open, the lifetime becomes longer. So a meson lifetime is not a mysterious temperament. It is a map of what transitions nature permits. There is also a simple energetic principle at work. Unstable particles tend to decay into lighter ones when allowed. The meson is a bound state with a certain mass. If there are lighter particles into which it can transform while respecting all conservation laws, that transformation can occur. The reason the proton is so special, as discussed earlier, is that no easy allowed decay route presents itself in the standard model. Mesons are usually not so fortunate. Many of them have perfectly good routes downward into lighter hadrons, photons, leptons, or combinations of these. So they do what unstable systems in physics generally do. They move toward allowed lower energy outcomes. One should not picture that as a deliberate decision, of course. Mesons are not glancing anxiously at an exit sign and heading for it. The decay is built into the quantum description of the state. An unstable particle does not sit there actively choosing whether today feels like a good day to become something else. Rather, its lifetime reflects the probability structure of the allowed transitions. Over many identical mesons, one can measure a characteristic lifetime. Any individual decay is probabilistic, but the statistical pattern is precise. This is another point where the quantum world is both unsettling and dependable. The exact moment of transformation is not predictable for a given single meson in the ordinary deterministic sense, yet the overall distribution is reliably measurable. There is also the matter of resonances, which adds another shade to the story of appearance and disappearance. Some mesons are not long-lived particles even by hadronic standards. They are resonant states formed in an interaction, and then decaying almost immediately through the strong interaction. In such cases, it can be more useful to think of the meson as a pronounced temporary configuration in the scattering process, rather than as an object one could meaningfully isolate. These resonances still count as mesons. They still have definite masses and widths in the appropriate sense. But their fleetingness reminds us that the particle concept in high-energy physics includes unstable states that live mostly as identifiable patterns in data, rather than as passengers travelling calmly through a detector. The width of such a resonance is closely connected to its lifetime. A broad resonance generally means a very short-lived state. A narrow one means a longer-lived state. This relationship is one of the practical tools physicists use when studying meson spectra. Again, the meson may appear and vanish too quickly to seem particle-like by everyday intuition, but in the mathematics and data of scattering theory it leaves a characteristic shape. Particle physics is remarkably good at learning from things that barely stay still long enough to be rude. The weak interaction adds further richness because it allows certain mesons not only to decay, but in some neutral cases to mix with their own antiparticle counterparts before doing so. Neutral kaons are a famous example. A neutral kaon and its antiparticle are distinct at the quark level, yet the weak interaction allows a more subtle time evolution in which the physical states that propagate are mixtures. This leads to lifetimes and decay patterns that are more intricate than one might expect from a simple particle label alone. Even without going deep into the formalism, the lesson's clear enough. Mesons do not always live as one uncomplicated identity from birth to decay. Sometimes the path from appearance to disappearance includes internal reshuffling of what the physical state effectively is. That same broad logic applies in the heavier meson sector too. Mesons containing charm or bottom quarks are especially useful because their decays can be studied in great detail. Different decay channels compete, some are more likely than others. Branching fractions can be measured. Tiny differences between matter and antimatter behaviour can be searched for. In these systems, mesons become precision tools for testing the standard model. Their appearance in a collider event is only the beginning. Their transformation patterns are where much of the scientific value lies. If a heavy meson decays in a way slightly different from what the theory predicts, people become very attentive very quickly. It is also worth asking why mesons appear so often in jets and hadronization, because this is one of the clearest practical expressions of confinement. When a high-energy quark or gluon is produced in a collision, it does not simply travel off and remain visible as a free-coloured particle. Instead, as it moves away, the colour field energy grows until quark-antiquark pairs are produced, and a whole spray of colour neutral hadrons forms. Mesons are abundant in this process because quark-antiquark pairings are one of the easiest ways to achieve colour neutral outcomes. So the appearance of mesons is not merely an occasional special event, it is woven into how quarks and gluons become observable hadrons at all. This is one of those wonderfully awkward truths that particle physics keeps insisting on. We talk about quarks because they are fundamental constituents of hadrons, yet what our detectors often record directly are hadrons, especially mesons and baryons, created from quarks and gluons as they hadronize. The fundamental entities are not usually seen naked. Their bound state offspring are. Mesons, in that sense, are among the visible grammar of the invisible theory. Another useful distinction is between real mesons and virtual mesons in effective descriptions. In many contexts, especially in nuclear theory, one may speak of meson exchange as part of the force between nucleons. These exchanged mesons are not always real on shell particles flying about in the same sense as a produced pion in a detector. They can be virtual carriers within the mathematical description of an interaction. This is helpful because it shows that mesons can matter both as actual detectable particles and as effective ingredients in how forces are modelled at larger scales. Appearance in physics is sometimes literal and sometimes part of an internal description of a process. Still, The real produced mesons are the ones that make the topic feel alive. A collision occurs, energy becomes hadrons, a meson is formed. It travels a tiny distance, perhaps measurable, perhaps not. Then it decays. Outward go photons, muons, neutrinos, other hadrons depending on the case. Detectors register tracks, showers, missing momentum, displaced vertices, timing signals. From these, physicists reconstruct what happened. The meson has appeared, transformed, and vanished, but not without leaving a traceable account of itself. There is something almost administrative about it. Even the shortest lived particles tend to file their paperwork through the detector. All of this makes mesons extraordinarily useful. Their transience is not a nuisance to be tolerated. It is part of what makes them informative. The way a meson appears tells you about the interaction that created it. The way it transforms tells you about the forces available for its decay. The way it vanishes tells you which final states are allowed and how likely each is. Its lifetime tells you which interaction dominates the transition. Its decay products tell you how to reconstruct its identity. A meson is not just a particle. It is a process condensed into a particle-shaped interval. And this is why mesons are some of the best teachers in all of particle physics. They are born often because the strong interaction loves to organize quark-antiquark content into hadrons. They change according to clear but varied rules, because different interactions mediate different decays. They disappear quickly enough to remind us that stability is not the norm everywhere, but neatly enough that the data can still be read. The meson is a fleeting object that behaves with almost unreasonable explanatory generosity. Once one sees mesons this way, the next question practically asks itself. If they're so short-lived and so often known only through what they leave behind, how do physicists actually detect them, measure them, and distinguish one meson from another inside the storm of particles produced in real experiments? Because the answer is not that someone peers into a machine and spots a polite little peon waiting to be introduced. The answer lies in tracks, energies, lifetimes, decay products, and the patient art of reconstructing something real from what vanished almost immediately. And this is where the whole subject becomes especially satisfying, because mesons may be tiny, short-lived, and impossible to observe with a naked eye in any direct ordinary sense. Yet physicists have become remarkably good at detecting them anyway. Not by watching little coloured particles drift through a microscope, of course. Nothing in particle physics is ever that accommodating. Instead, detection is a matter of reading consequences. A meson is known by the path it takes if it lives long enough, by the particles it decays into if it does not, by the energy it deposits, by the timing of its arrival, by the curvature of a track in a magnetic field, and by the statistical pattern it leaves when many events are examined together. In other words, physicists detect something so small by building instruments that do not ask the meson to introduce itself, but instead force the universe to leave evidence. This is one of the quiet conceptual shifts that people often have to make when they first begin thinking seriously about particle physics. In everyday life, to detect something usually means to see it, hear it, touch it, or perhaps at least watch it move around. In particle physics, direct sensory intuition is almost entirely out of its depth. Mesons are too small and too fleeting for that kind of encounter, so the meaning of detection changes. To detect a meson is not necessarily to watch the meson itself as a lasting object. It is to measure an event in which the meson participated and then reconstruct, from the available evidence, that the meson must have been there. That word, reconstruct, is doing a great deal of work. Modern particle physics often operates less like looking and more like forensic reasoning at extraordinary speed. A detector records signals. Some correspond to charged particles leaving tracks. Some correspond to showers of energy in dense materials. Some correspond to particles passing through outer layers with very little interference. Some correspond to momentum that seems to be missing because a neutrino carried it away without interacting much. From all of this, physicists piece together what happened in the collision. If the pattern matches the known signature of a meson, then the meson has effectively been detected, even if it lived for only the briefest instant before decaying. It helps to begin historically, because the older detectors make the logic easier to visualize. Early particle physicists used devices such as cloud chambers, bubble chambers, and photographic emulsions. These instruments did not display particles as tiny solid objects. They displayed the disturbances particles caused while moving through a medium. In a cloud chamber, a charged particle passing through supersaturated vapor would leave behind a visible trail of droplets. In a bubble chamber, a charged particle moving through superheated liquid would seed a line of tiny bubbles. If a magnetic field was present, the track would curve, and the curvature would tell you something about the momentum and charge of the particle. If the track suddenly kinked or branched, that could indicate a decay. If two tracks emerged from one point, perhaps a neutral particle had decayed there into charged products. Physicists learned to read these photographs like weather maps of invisible events. There is something charming about those older methods because they made particle physics look almost handmade. A meson could leave its signature in a bubble chamber photograph, and the evidence would sit there as a graceful curved line in a picture. It still required theory, care, and a great deal of caution to interpret, but the image had a kind of visual drama that modern detectors often hide behind electronics and software. Even so, the principles remain continuous. Whether the signal is a line of bubbles or a digital record in a tracking system, the task is the same. One must infer the unseen particle from its effects. Charged mesons are easier to track directly than neutral ones, at least at first, because a charged particle moving through matter ionizes atoms along its path. That ionization can be measured. In a modern detector, the particle may pass through layers of silicon or gas-filled tracking chambers, leaving tiny electrical signals behind. These signals mark points in space, and a computer reconstructs the path from them. If the detector sits inside a magnetic field, the track curves. The direction of the curve tells you the sign of the electric charge. The degree of curvature tells you the momentum. So a charged pion or charged kaon can be detected by the track it leaves while it is still intact, assuming it survives long enough to cross part of the detector before decaying. This is one reason magnetic fields are so useful in particle experiments. A charged particle in a magnetic field does not travel in a straight line unless its momentum is extremely high compared with the field strength. It bends. That bend is not just a pretty flourish, it is information. By measuring the curvature carefully, physicists can infer how much momentum the particle had. If the charge is known from the bend direction, and the momentum is known from the bend size, then the particle is already much less anonymous than it was a moment before. But momentum alone does not tell you whether the track belongs to a pion, a kaon, a proton, or something else. For that, one usually needs additional clues. One important clue comes from how much energy the particle loses as it passes through the tracking material. Different kinds of particles moving at the same momentum can deposit energy differently because their masses differ. Another clue can come from timing. If a particle takes slightly longer to cross a known distance that can help determine its speed, combine the speed with the momentum and you gain insight into the mass. This is the basis of time-of-flight methods, which are exactly what they sound like, though executed with absurd precision. When the particles are moving close to the speed of light, the timing differences are tiny, but modern detectors are not easily discouraged by tiny things. There are also Cherenkov detectors, which rely on a lovely effect that sounds almost too elegant to be practical. When a charged particle travels through a medium faster than light can travel through that same medium, it produces a cone of light, somewhat analogous to the shock wave of a supersonic aircraft. The angle of that light depends on the particle's speed. So again, if the momentum is known and the speed is measured, the particle identity becomes easier to infer. This is one of those moments in physics where the instrument sounds so clever that you almost suspect the universe has agreed to be cooperative for once. A meson rushes through the detector, light appears at a measurable angle, And from that angle, physicists learn something about what just passed through. Calorimeters provide another major piece of the puzzle. These are detector components designed to absorb particles and measure the energy they deposit. Electromagnetic calorimeters are particularly good at handling electrons, positrons and photons, while hadronic calorimeters are built to deal with hadrons such as protons, neutrons, pions and kaons. If a meson reaches the calorimeter before decaying, or if its decay products enter the calorimeter, the resulting shower of interactions can be measured. The total deposited energy, the shape of the shower, and its location all help identify what happened. A neutral pion, for example, often decays rapidly into photons, and those photons can create electromagnetic showers in the calorimeter. From the energies and directions of those showers, one can reconstruct that a neutral pion was the parent. That idea of reconstructing a parent from its daughters is one of the most important techniques in particle physics. Many mesons decay too quickly to leave an extended track of their own. Instead, what detectors actually record are the decay products. If those products match a known pattern, then the meson can be identified statistically and often event by event. Suppose a neutral meson decays into 2 photons. The detector records 2 electromagnetic energy deposits. Their directions are measured, their energies are measured. From that information, one can calculate the effective mass of the original particle that would have produced them. If a large number of such events pile up around the known mass of a neutral pion, then the neutral pion has announced itself with all the subtlety of a repeated statistical confession. This statistical aspect is worth lingering over, because it is deeply characteristic of the field. Physicists do not usually identify mesons by one magical unmistakable event, and then retire for tea. They often identify them by examining thousands, millions, or even billions of events, and looking for patterns that rise above background noise. A certain combination of particles appears again and again. The reconstructed mass forms a peak at a particular value. The decay distance distribution matches a known lifetime. The angular distributions match expected quantum properties. Over time, certainty emerges not from one perfect sighting, but from the accumulation of many consistent clues. This does not mean individual events are unimportant. Some are extraordinarily informative, but the discipline as a whole relies on the fact that unstable particles reveal themselves through repeatable statistical behaviour. A meson is not identified only because it could have been there. It is identified because the data behave exactly as they should if it was there, and because competing explanations fail to account for the same pattern as neatly. Short-lived mesons create another useful signature through what are called displaced vertices. If a particle is produced at one point in a detector and then decays a measurable distance away, the daughter tracks may seem to originate not from the primary collision point, but from a secondary location. That secondary location is the decay point. For some heavier mesons, especially those involving bottom or charm quarks, the lifetime is long enough by particle standards that this displacement can actually be measured with exquisite tracking systems. Silicon vertex detectors are particularly good at this. They sit very close to the collision point and record particle trajectories with extraordinary precision. If the tracks of decay products can be traced backward to a point slightly offset from the primary interaction, that is a strong clue that an unstable particle travelled briefly before decaying there. This is one of the ways heavy mesons are identified in modern experiments. There is something almost detective novel-like about this. A collision occurs. Most tracks emerge directly from the scene, but a few appear to begin a small but measurable distance away. That suggests an intermediate particle was produced, lived briefly, and then decayed. The direction of travel, the decay products, the reconstructed mass, and the displacement together tell the story. The meson was never seen in the everyday sense, yet its passage is written into geometry. Neutral mesons are often trickier because they do not ionize material directly in the way charged particles do. They leave no neat charge track through the detector. Instead, they are inferred through what they decay into, or through the energy they deposit when they interact. Neutral pions, as mentioned earlier, often reveal themselves through photon pairs. Neutral kaons can be more subtle because they come in long-lived and short-lived forms with different decay patterns. Some neutral mesons can travel some distance before decaying into charged particles, which then leave tracks that point back to a displaced vertex. Others decay into combinations involving photons, leptons, or hadrons. The neutral meson itself remains elusive, but its fingerprints are all over the apparatus. Muons deserve a brief mention here because they often appear in meson decays and are unusually easy to identify in many detectors. Unlike strongly interacting hadrons, muons tend to pass through large amounts of material with relatively little absorption. So modern detectors often have outer muon systems designed specifically to recognize them. If a meson decay produces a muon, that can be extremely useful. Certain heavy mesons, for instance, may decay into pairs of muons or into a muon plus other products, and those clean muon signatures can make the original meson easier to reconstruct amid the surrounding clutter. In a very crowded event, a muon can behave like the one person in a chaotic room who remembered to wear a bright coat. The clutter itself is a serious part of the challenge. High-energy collisions do not usually produce one polite meson at a time in an otherwise empty chamber. They produce a great deal of activity. Many particles emerge. Background processes mimic some of the same signatures. Radiation, noise, overlapping events, and unrelated tracks all complicate the picture. So detecting a meson is never just a matter of having a sensitive enough instrument. It is also a matter of filtering, pattern recognition, calibration, and statistical discipline. One must know what the detector does when a pion passes through, how a kaon differs, how photons shower, how muons penetrate, how often random combinations fake a signal, and how to subtract background honestly without subtracting the thing one hopes to study. That is why modern particle experiments depend as much on software and data analysis as on the hardware itself. The detectors generate enormous amounts of information. Trigger systems decide in real time which events are interesting enough to keep. Reconstruction algorithms convert raw signals into tracks, vertices, and energy clusters. Particle identification routines combine different measurements to decide whether a given track is most likely a pion, a kaon, a proton, or something else. Statistical tools then separate signal from background and measure the properties of the resulting particle sample. By the time a plot reveals a meson peak, an extraordinary amount of work has already happened behind the scenes. Calibration is especially important because the detector must be understood in detail before it can be trusted. Physicists use well-known processes and particles to check that the momentum scale is right, that the timing is accurate, that the calorimeter response is stable, and that the reconstruction does not introduce bias. If a detector mismeasures energies slightly, reconstructed masses shift. If timing drifts, identification becomes less reliable. So the art of detecting mesons is partly the art of making sure the instrument tells the truth consistently. Particle physics is very often a triumph of disciplined measurement over the natural tendency of complicated machines to be slightly temperamental. There is also a beautiful reciprocity between theory and detection. The theory predicts which mesons should exist, how they should decay, what their masses and lifetimes should roughly be, and how they might be produced. The detector then looks for the corresponding signatures. If the signal appears where expected, confidence grows. If something unexpected appears, curiosity sharpens. Many new mesons and meson-like states have been found, precisely because a detector revealed a statistically significant excess in a particular combination of decay products. At first, it may look like a bump in a spectrum. Then it survives more data, more analysis, more scrutiny. Eventually, the community accepts that a new state has been seen. So sometimes a meson is detected not because people already knew exactly where to look, but because the data developed an unexplained habit that would not go away. A great many mesons have been discovered this way, especially in the heavy quark sector. A collider produces enormous numbers of events. Analysts reconstruct combinations of particles that might come from a parent state. they plot the reconstructed masses. Most combinations form a smooth background, but if a real parent meson is being produced and decaying into that final state, the plot shows an excess around the parent mass. With enough resolution and enough events, the excess becomes unmistakable. It is one of the most quietly thrilling sights in experimental physics, a peak rising from the noise, announcing that an unstable particle has been caught by its consequences. Different experiments are optimized for different kinds of mesons. Some detectors are built to study the debris of very high-energy proton collisions, where mesons of many types are produced abundantly. Others are designed for cleaner electron-positron collisions, where the environment is less cluttered, and certain meson states can be studied with greater precision. Fixed-target experiments, neutrino experiments, and heavy ion experiments each produce and detect mesons in different ways. So there is no single universal method. The general logic is shared, but the practical details depend on what kinds of events the experiment is built to explore. Heavy ion collisions add another layer because they create extremely hot, dense environments in which many hadrons, including mesons, are produced. Studying which mesons appear, how many, and with what momenta can reveal something about the medium created in the collision, including the possible formation of quark-gluon plasma. In such experiments, mesons are not only objects of interest in themselves, but also probes of a broader state of matter. Once again, detection becomes a conversation between what the meson is and what the meson has passed through. Even in more modest laboratory settings, mesons have practical signatures. Charged pions and kaons can be distinguished by a combination of momentum, timing, and energy loss. Neutral pions can be identified through photon pairs. Heavy flavor mesons can be recognized through displaced decays and characteristic daughter particles. Resonances can be identified through peaks in mass distributions. The methods differ, but the underlying philosophy remains consistent. One measures what the meson does, what it becomes, and what traces it leaves in matter and data. So when people ask how physicists detect something so small, the answer is both simple and elaborate. Simple, because the core principle is always to measure interactions and infer the particle from them. Elaborate, because building the instruments and analyses capable of doing this reliably is one of the great technical achievements of modern science. Detectors are not giant eyes. They are layered systems of materials, electronics, magnetic fields, timing devices, and software, all designed to turn invisible particle behavior into measurable evidence. A meson does not have to be seen in the everyday sense to be known. It only has to leave a pattern that the laws of physics and the detector together can make legible. And this, in a way, is one of the most impressive things about particle physics as a whole. It studies a realm far too small for ordinary perception, yet it does so with methods that are not mystical at all. A track curves, a shower deposits energy, a vertex appears displaced, a timing signal arrives, a mass peak forms in the data. Bit by bit, a short-lived meson becomes a documented fact. It appeared, transformed, and vanished, but not before giving the experiment enough information to recognize it. Once that machinery of detection is in place, mesons stop being merely abstract quark-antiquark states and become active tools for exploring where and how the universe behaves at its most energetic. They turn up in collider debris, in cosmic ray cascades, and in the conditions that once filled the early universe, which is why the next part of the story naturally moves outward from the detector and asks where mesons matter most on the largest physical stages available. And once physicists learned how to detect mesons reliably, those particles stopped being merely brief curiosities in a detector and became something much larger. They became tools for reading some of the most energetic environments in nature. A meson can be born in a collider, produced high above your head in the atmosphere by a cosmic ray, or formed in the unimaginably hot conditions that filled the universe shortly after its beginning. In each of those settings, mesons tell a slightly different story. In colliders, they reveal how quarks and gluons behave when energy is concentrated into very small regions. In cosmic rays, they connect high-energy particle physics to the sky above us. In the early universe, they help us think about what matter was doing before atoms, before nuclei settled into their familiar forms, and before the cosmos became quiet enough for the ordinary substances of daily life to exist. Let us start with colliders, because they are the most deliberate Meson factories humanity has ever built. A collider is, at heart, a machine for turning motion into insight. Particles are accelerated to extremely high energies and then brought into collision. That sounds simple when said quickly. In practice, it is one of the grand engineering habits of modern civilization, a way of taking tiny constituents of matter and persuading them to reveal their deeper structure by smashing them together with enough precision that the aftermath can be measured in ridiculous detail. It is not the most peaceful way to learn about the universe, but it has been very productive. When particles collide at high energies, mesons appear in abundance. This is especially true in hadron colliders, where protons are accelerated and then sent into one another at tremendous speed. A proton is not elementary. It is already a busy composite object filled with quarks, antiquarks, and gluons. So when two protons collide, the event is really a swarm of possible constituent interactions. Quarks scatter off quarks, gluons interact with quarks, gluons interact with other gluons, energy piles up, and from that energy new quark-antiquark pairs can be created. Because of confinement, those quarks and antiquarks do not emerge as free particles. They hadronize, reorganizing into color-neutral bound states. Mesons are among the most common outcomes of that reorganization. This means that if you stand back and think about what a hadron collider really produces, the answer is often a great deal of mesonic traffic. Pions are plentiful, kaons are common. Heavier mesons appear when the collision energy and the internal parton interactions allow it. Charmed mesons, bottom mesons, and a whole variety of short-lived resonances can be formed. Much of the challenge in experimental particle physics is not making mesons happen. Nature is generous on that front. The challenge is identifying which mesons were produced, how often, in what states, and through which processes. That abundance is not a nuisance, it is a major source of information. Light mesons such as pions and kaons help physicists understand how quarks and gluons hadronize after a hard collision. Heavy mesons are especially valuable because they can act as precision probes of the standard model. A meson containing a charm quark or a bottom quark has a more distinctive identity, a set of measurable decay channels, and a lifetime that can often be studied in detail. Those properties make such mesons excellent for testing calculations, searching for rare processes, and checking whether matter and antimatter behave exactly as expected. There is something very useful about the fact that mesons are both common and varied. Common particles are helpful because there is plenty of data. Varied particles are helpful because each type emphasizes a different aspect of the theory. A light pion tells you something about low-mass hadron production and the way the strong interaction shapes the most basic meson sector. A neutral kaon can tell you about mixing and weak decays. A meson containing a bottom quark can tell you about flavor physics, rare transitions and subtle symmetry effects. So in collider experiments, mesons are not only products, they are instruments, though admittedly instruments, with the unhelpful habit of decaying before one has fully introduced oneself. Electron-positron colliders provide a slightly different environment, and that difference matters. When an electron and a positron collide, the initial state is much cleaner than in a proton collision because the incoming particles are elementary, at least as far as current evidence shows. There is less internal clutter to account for. That makes certain kinds of meson studies especially precise. Specific energy settings can favour the production of particular meson families or resonances, and the resulting events can be easier to interpret than the dense hadronic spray of a proton collision. If the hadron collider is a noisy market square full of possible conversations at once, the electron-positron collider can feel more like a carefully arranged interview, where the background interruptions have at least been asked to lower their voices. Mesons also matter greatly in heavy ion collisions, where entire atomic nuclei are accelerated and smashed together. These events create conditions of extraordinary temperature and density for a very brief time. In that environment, the usual hadronic boundaries can melt into a state known as quark-gluon plasma, where quarks and gluons are no longer confined into individual hadrons in the ordinary way. As this hot matter cools and expands, hadrons form again, and mesons are part of that process. By studying which mesons are produced, how many appear, how much momentum they carry, and how heavy quark mesons survive or are suppressed in the medium, physicists learn about the behaviour of strongly interacting matter under extreme conditions. This is one of the places where mesons become more than particles and more than decay signatures. They become thermometers, clocks, and witnesses. Different mesons respond differently to the medium created in a heavy ion collision. Some may be dissolved more easily by the hot plasma. Some may be regenerated as the system cools. Some may carry information about collective flow, telling researchers how the plasma expanded and moved. So once again, the meson proves remarkably versatile. It is a bound state, a signal, a probe, and a test of theory all at once. Now let us leave the Collider Hall entirely and look upward, because mesons are not only made by human machines. The universe has been running its own high-energy physics program for a very long time. Cosmic rays, which are high-energy particles arriving from space, constantly strike the atmosphere of Earth. When they do, they collide with nuclei in the upper air and produce cascades of secondary particles. Those cascades include many mesons, especially pions and kaons, so even as you sit indoors, perhaps quite peacefully, and with no particular intention of joining a particle experiment, mesons are being created above you in the atmosphere as part of the ongoing traffic between Earth and the wider cosmos. This fact is oddly comforting in a very technical way. It means the sky is not merely scenery, it is also a particle source. Long before accelerators reached the energies now familiar in laboratories, cosmic rays gave physicists access to processes energetic enough to reveal new particles. Much of the early history of the particle zoo depended on this atmospheric gift. Mesons were among the particles discovered or studied through cosmic ray events, and even today cosmic rays continue to provide natural laboratories for energetic interactions. The chain of events is worth following slowly because it shows how mesons connect outer space to life on the ground. A high-energy cosmic ray, often a proton, enters the atmosphere and strikes an atomic nucleus. That interaction produces hadronic debris, including pions and kaons. The charged pions and kaons then decay, often producing muons and neutrinos. The muons are relatively long-lived by particle standards, and interact weakly enough with matter that many of them reach the surface of Earth. In fact, muons produced high in the atmosphere are constantly passing through you and everything around you. Not in a dramatic way, and not in a way that requires alarm, but in a quiet and steady way that says the atmosphere is part of a very large particle chain. Mesons are central to that chain. Without the atmospheric production of pions and kaons, the familiar rain of cosmic muons at the surface would look very different. So when physicists study cosmic ray showers, they are not only learning about the cosmic rays themselves, they are also studying how mesons are produced and decay in the atmosphere. The details matter. The ratio of pions to kaons affects the resulting muon and neutrino fluxes. The energies of the mesons influence how far they travel before decaying. The competition between decay and further interaction in the atmosphere changes the final particle distribution. Mesons, once again, are not peripheral. They are the main intermediaries through which the story unfolds. Neutrino physics, interestingly enough, owes quite a lot to mesons for this reason. Many neutrino beams in experiments are created by producing pions and kaons in collisions and then allowing them to decay. The resulting neutrinos are directed toward detectors that may be near or far away. This means mesons help make neutrino experiments possible in a practical sense. They are the parents of the beam. In the atmosphere, they do something similar without asking permission from anyone. They create natural neutrino fluxes that travel through Earth and into large underground detectors. So if a neutrino physicist seems unusually appreciative of humble pions and kaons, there is good reason for it. The beam does not happen without them. There is also a broader astrophysical point here. Cosmic ray interactions involve energies and conditions that can exceed what many laboratory setups routinely explore. By studying the mesons and later particles produced in these showers, physicists can test models of hadronic interaction at high energy. This matters because when interpreting cosmic ray observations, one needs to understand what happens when the incoming particle strikes the atmosphere. The cascade is not just a mess to be tolerated, it is a physical system to be modelled. Mesons sit at the centre of that modelling because they are among the dominant hadronic products and decay sources. It is quietly remarkable that one and the same type of particle can be studied in such different settings. In one case, an accelerator team has built an entire machine, aligned magnets, calibrated detectors, and designed triggers to catch Meson events. In another case, the upper atmosphere and a cosmic ray from some distant astrophysical source have done the production for free. The Meson does not much care which arrangement gave rise to it. It follows the same laws either way. That consistency is one of the reasons particle physics can connect the laboratory to the sky so effectively. And now the scale changes again, because if colliders show us how mesons behave in carefully prepared experiments, and cosmic rays show us how they arise in natural high-energy events overhead, the early universe asks us to imagine conditions far more extreme than either. There was a time, shortly after the beginning of cosmic expansion, when the universe was so hot and dense that familiar atoms did not exist. Nuclei did not yet exist in stable abundance. Even hadrons as enduring objects were not always the right language. Matter was in a far more energetic state. To think about mesons in that setting is to think about an era when the strong interaction was still playing out in a plasma-like environment, and the basic ingredients of hadronic matter were only gradually settling into the forms that later became familiar. At very early times, the universe was too hot for hadrons such as protons, neutrons, and mesons to survive as stable-bound states in the usual sense. The energy density was so high that quarks and gluons moved in a deconfined medium. In that regime, one does not really have a gas of pions or kaons drifting about like very small weather. One has a quark-gluon plasma. But as the universe expanded and cooled, there came a stage when confinement reasserted itself and hadrons formed. Mesons would have been part of that transition. They belonged to the menu of allowed-bound states once the temperature dropped enough for quarks and gluons to organize into color-neutral particles. This does not mean the early universe settled down immediately into the familiar matter around us. There were still annihilations, decays, weak interaction processes, and the gradual emergence of the particle abundances that later shaped nuclear synthesis and atomic matter. Mesons in that environment were often temporary, because the surrounding conditions still allowed many interactions and transformations. But temporary is not unimportant. Their presence tells us what the particle content of the universe looked like during those early stages, and how strongly interacting matter behaved as the cosmos cooled. The pion is especially useful in thinking about the later parts of this era, when the temperature had fallen enough that hadrons existed, but the universe was still a very busy place. Pions, being the lightest mesons, can dominate aspects of the hadronic population in thermal settings. In nuclear and hadronic matter at sufficiently high temperature, pions are often among the most relevant mesonic degrees of freedom. They affect thermodynamics, interaction rates, and the way energy is distributed among hadrons. So in the early universe, once hadrons existed as meaningful states, pions would not have been mere decorative extras. They would have been among the principal mesonic participants. There is an appealing symmetry here between the early universe and heavy ion collisions. In both cases, one is dealing with strongly interacting matter under extreme conditions. In both cases, quark-gluon plasma and hadronization become important ideas. In both cases, mesons emerge as part of the cooling and reorganization of matter. Heavy ion collisions last for only a tiny fraction of a second and occur in a laboratory detector. The early universe lasted longer and involved all of space. but the underlying physics has enough overlap that one can think of collider studies as offering small brief glimpses of conditions that once filled the cosmos on the largest scale imaginable. Mesons also matter indirectly in the story of why the universe ended up with the matter content it has. Certain Meson systems, especially those involving strange and bottom quarks, have been central to studying violations of symmetries between matter and antimatter. Those symmetry violations are not by themselves enough to explain the full cosmic imbalance that allowed matter to dominate over antimatter, but they are part of the broader picture of how the laws of physics distinguish the two in subtle ways. So while pions and kaons in the early universe were not deciding the cosmic future in some dramatic individual sense, the physics learned from Meson decays in laboratories is part of the effort to understand why anything solid exists to ask the question at all. This is one of the reasons Mesons remain so interesting. They belong to small-scale physics and big-scale questions at the same time. A meson can be a tiny, short-lived product in a detector event, and yet the theory required to understand it helps describe the behavior of matter in the early universe. It can be produced in the atmosphere by a cosmic ray, and the same decay logic that explains that shower helps physicists design neutrino beams and interpret astrophysical observations. It can arise in a collider and vanish before crossing much of the apparatus, and still teach us something about confinement, flavor physics, or the hottest matter humans have ever created. So mesons are not just local curiosities of the subatomic world. They are part of a much larger map. They belong to the controlled violence of colliders, the natural violence of cosmic rays, and the primordial violence of the young universe. In each environment they appear for a reason. The strong interaction turns available energy into hadronic states. Quarks and gluons reorganize, bound states form. Mesons show up because they are among the simplest and most natural outcomes of that reorganization. Then they decay, transform, or help describe what the surrounding medium was like. Their lives are brief, but their usefulness spans an extraordinary range, and that wide range brings the whole discussion back to the original question in a more satisfying form. By now, the meson is no longer just a definition about one quark and one antiquark. It has become a participant in collider physics, a link in atmospheric cascades, and a clue to the earliest stages of matter in the cosmos. Which means the final step is not simply to repeat what a meson is made of, but to gather everything together and answer more clearly what a meson really is when all of these pieces are allowed to speak at once. By this point, the question has changed shape a little, which is usually a good sign in physics. At the beginning, asking what a meson is really made of can sound like a request for a short, clean answer. Perhaps one imagines that the meson is built from one thing or two things, and once those things have been named, the matter is settled. But after following mesons through the particle zoo, through quarks and antiquarks, through the strong force and the gluons that bind, through pions and kaons, and the busy interior life of hadrons, it becomes clear that the answer has layers. The simplest layer is still true. A meson is made of a quark and an antiquark. That is the starting point, and it is not a misleading one. It tells you what kind of hadron a meson is. It tells you how it differs from a proton. It tells you why it belongs to one branch of the particle family tree rather than another. But it is not the whole answer, and the phrase really made of asks for the whole answer. If someone asked very casually, while waiting for the kettle to boil, or pretending not to be alarmed by how much particle physics can fit into one evening, the neat version would do perfectly well. A meson is a quark and an antiquark bound together by the strong interaction. That sentence is brief, respectable, and fundamentally correct. It will get you quite far. It explains why pions are mesons. It explains why kaons are mesons. It explains why mesons belong to the hadron family, and why they are different from baryons like the proton and neutron. There is nothing wrong with that answer. The problem is only that nature, as usual, refuses to stop exactly where the first good answer ends. A meson is not just a quark and an antiquark in the way a sandwich is just bread and filling. It is not a tiny object with two little pieces sitting quietly inside it, while the rest of the interior politely remains empty. The quark and antiquark are the valence content. They define the main identity of the particle. They are the reason a given meson is a pion rather than a kaon, or a kaon rather than a heavier meson involving charm or bottom. But the full physical meson includes more than that. It includes the gluon field that binds the pair together. It includes the energy stored in that binding. It includes the internal motion of the constituents. It includes the sea of temporary quark-antiquark pairs that can appear as part of the quantum activity inside the hadron. So when you ask what a meson is really made of, the truthful answer has to include both the defining ingredients and the dynamic structure that makes those ingredients into a particle. That difference matters. In daily life, being made of something usually means there is a stable material that can be listed in simple terms. A mug is made of ceramic. A table is made of wood. A shirt is made of cotton. The item may have shape, colour, texture, and design, but its material composition sounds straightforward. At the level of hadrons, and mesons in particular, made of becomes a more difficult phrase because the internal content is not static, and the binding itself contributes to what the object is. The meson is not merely assembled from ingredients, it is sustained as a bound quantum state by the strong interaction. That may sound like a more technical way of saying the same thing, but it is not quite the same. It means the meson is as much about the relation between its constituents as it is about the constituents themselves. This is where the valence quarks come back into focus. The valence pair is still central. If you strip the description down to its skeleton, a meson has one quark and one antiquark as its main defining structure. That is what puts it in the meson category at all. A proton has 3 valence quarks. A meson has one quark and one antiquark. That distinction is not decorative. It shapes the particle's charge possibilities, its statistics, its role in matter, and the way it behaves under the strong interaction. So one should not overcorrect and pretend the valence content is some outdated simplification. It remains absolutely essential. Without it, the meson loses its identity. Even so, if you stop there, you miss the gluons. And missing the gluons in a meson is a bit like describing a thunderstorm as a collection of raindrops, while quietly skipping the atmosphere. Gluons carry the strong interaction. They bind the quark and antiquark together. More importantly, they are not passive messengers. Because they carry the relevant charge of the strong interaction themselves, they interact with one another. This makes the strong force unlike electromagnetism in a very important way. The field is active, self-involved, and intensely non-trivial. The meson is therefore not simply a quark on one side and an antiquark on the other, with a quiet connection between them. It is a strongly interacting field system. The gluons are part of what the meson is, not merely a service provided from outside. That point helps explain why the mass of a meson is not usually just the sum of the quark masses. In fact, for light mesons especially, the bare masses of the valence quarks are only a small part of the total story. Much of the mass comes from the energy of the strong interaction itself, including the internal motion and binding. So if someone says a pion is made from light quarks, that is correct, but it does not mean the pion mass can be understood as little more than 2 tiny masses placed side by side. The meson gets much of its physical substance from the energy locked into its quantum state. In other words, it is made not only of particles but of interaction energy that cannot be peeled away from those particles without destroying the state entirely. Then there are the C quarks. These are the temporary quark-antiquark pairs that arise from the ongoing quantum behaviour of the gluon field. They do not define the meson in the same way the valence pair does, but they are part of the meson's full internal structure. This can sound annoying at first, because it complicates the answer just when the answer had finally started behaving. But it is an honest complication. The interior of a hadron is not a quiet chamber. It is a quantum system in which additional pairs can appear and disappear as part of the normal activity permitted by the theory. If you probe the Meson deeply enough, that activity matters. Momentum is shared among valence quarks, gluons, and C contributions. Certain measurable properties depend on the full internal structure, not just the defining pair. So a meson is really made of a valence quark and antiquark, immersed in a sea shaped by gluons and quantum fluctuations. Motion belongs in that sentence too. Quarks inside a meson are not resting like little marbles in a box. They are confined, yes, but confinement is not the same as stillness. Their motion is part of the bound state. Their relative arrangement can involve different spin combinations and orbital motion. The Meson spectrum reflects these possibilities. One set of quark flavors can give rise to several meson states depending on how the internal quantum numbers are arranged. So even with the same basic valence ingredients, the full meson can differ because the internal motion and configuration differ. This is why meson spectroscopy is a rich subject. The particle is not defined by flavor alone. It is defined by the full allowed state of the quark-antiquark system under the rules of quantum chromodynamics. At this stage, the word thing starts to become a little slippery. Is a meson a thing in the ordinary sense? Yes, in that it has measurable mass, lifetime, momentum, and decay channels. It appears in experiments. It leaves signatures in detectors. It can be counted statistically and studied in detail. No, in the sense that it is not a small rigid object with permanent visible subparts, arranged in a stable geometric way. A meson is better understood as a color-neutral bound state, a particle defined by an allowed pattern of quark, antiquark, gluon, and field activity. That may sound more abstract than calling it a tiny object, but it is also more accurate. Physics sometimes asks us to give up a familiar picture in order to gain a truer one. This is also why the question of what a meson is really made of cannot be separated from the question of how mesons appear and disappear. A meson is not part of the long-lived furniture of ordinary matter in the way protons are. Most mesons are unstable. They are produced in energetic processes and then decay into other particles according to the conservation rules and available interactions. That transience is not a side note. It is part of what the meson is. A meson exists as a bound state that can be formed under the strong interaction and then transformed through strong electromagnetic or weak processes depending on the case. So the meson is not only made of constituents, it is also made of possibilities. The routes by which it can decay are built into its identity. A neutral pion, for instance, is not only a particular light quark-antiquark state, it is also a particle with a very characteristic decay pattern into photons. A kaon is not only a strange containing meson, it is also a particle whose weak decays and mixing behaviour taught physicists profound lessons about symmetry and flavour. A heavy meson involving charm or bottom is not only a quark-antiquark pair with greater mass. It is also a laboratory for testing the standard model through rare decays, lifetimes, and precision measurements. So in practice, what a meson is made of includes not only what lives inside the bound state at one moment, but how that bound state fits into the larger network of interactions. This is one reason mesons are so scientifically valuable. They are simple enough to define and complicated enough to teach. They are among the smallest conventional hadrons, yet they already force you to confront almost everything interesting about the strong interaction. Quark flavor matters, antiquarks matter, color neutrality matters, gluons matter, C-quarks matter, motion matters, binding energy matters, decay channels matter. The meson is small, but it is not conceptually modest. There is also a useful contrast here with the older mechanical view of matter. In that older habit of thought, understanding an object meant finding smaller hard pieces that composed it. You kept breaking things down until you reached something indivisible, and then you felt perhaps a little triumphant and perhaps ready for lunch. Modern particle physics did not end up following that script quite so neatly. Quarks appear to be elementary as far as current evidence shows, yes, but the hadrons made from them are not best understood as piles of tiny, hard lumps. They are quantum states. The field picture matters from the beginning. Interaction energy is part of the content. Confinement means the constituents do not appear in isolation. So a meson is not a miniature version of a macroscopic assembled object. It belongs to a different conceptual style of reality. That can feel unsatisfying at first if one is hoping for the comfort of a clean final piece, a last indivisible nugget that settles the matter forever. But there is another kind of satisfaction available here, and it is probably the better one. The Meson shows that the universe is not obliged to organize itself according to the mental habits we developed from spoons, tables, and teacups. At very small scales, what exists is often defined as much by interaction as by inventory. The Meson is a bound state because the strong interaction permits and enforces it. Its identity comes from its valence quark and antiquark, but its physical substance comes from the full quantum dynamics that bind and animate them. So if the question is asked very plainly, what is a meson really made of, the most complete plain answer might go something like this. A meson is really made of one quark and one antiquark as its defining valence constituents, together with the gluon field that binds them, the interaction energy that gives much of the particle its mass and structure, and the sea of transient quark-antiquark pairs that contribute to the full quantum state. It is not a static little object with two ingredients inside. It is a dynamic color-neutral hadron whose existence depends on confinement and the strong interaction. That is a longer answer than people usually bargain for, which may be why introductory books start with the shorter one. But the longer answer has the advantage of being faithful to what physicists have actually learned. And perhaps the most satisfying part is that this layered answer does not weaken the original simplicity, it enriches it. Saying a meson is a quark and an antiquark is still right. It is the doorway into the subject. The fuller picture simply reminds you that in physics, especially at the level of hadrons, a doorway is not the same thing as the whole house. Behind that first sentence lies a world of gluons, confinement, symmetry, C quarks, internal motion, decay patterns, collider signals, atmospheric showers, and the memory of conditions from the early universe. All of that belongs to what a meson really is. So in the end, the meson turns out to be both simpler and stranger than one might expect. Simpler because its defining valence structure is just a quark and an antiquark. Stranger because those two are never alone in the full physical sense, never quiet, never separable from the force that binds them. A meson is not only made of particles, it is made of a relationship that the strong interaction keeps enforcing. It is made of confinement, it is made of motion and field energy. It is made of a theory that becomes visible for a moment whenever one of these short-lived particles appears and leaves its trace in the world. And once you start seeing mesons that way, the question stops sounding like a request for ingredients and starts sounding like what it really was all along. A question about how nature builds things when the ordinary idea of building is no longer enough.